Yay. We're back. Everyone's back. Share my screen. Okay. Share. And chat. Someone said something. Good evening, Yash. Cool. Vaishnavi, Surabhi, Shobit. Excellent. Okay, everybody. So now let's actually just talk for just a couple of minutes and then we can talk about transactions and distributed transactions. Shobit, deep. So tell me about your homework. What does homework 2 look like? There's all sorts of questions I see on Piazza. Very interesting questions. It tells me the wheels are spinning in your heads. In general, any comments about the homework? Not specific questions like, can I, do this? Can I do that? Those you can ask on Piazza. But what do you think about the homework? It's not too trivial, right? First of all, you don't get it done in 5 minutes. And I hope you think that's okay. Because this is USC after all, right? We can't just make it like too simple and then it looks laughable. So someone shouldn't look at that and go, wow, is that all they're teaching them? So it shouldn't be like that. But it's not horribly hard as well. It is not something that take days and days just to get started. It has lots of pieces to it, some of them, but they're not difficult. Yeah, exactly, that is true. Yeah, the thing that you observed is quite interesting. I could have easily made these tables for you guys, right? But in a way, it is cool to start with a design, literally the ER diagram, and actually create the database. But you don't have to populate your database with hundreds of patients, hundreds of doctors. Just have small enough numbers, rows that can get the query done for you. Because you're trying to demonstrate feasibility, that's all it is. So I wouldn't kill myself making my database be massively large. The tables don't have to have hundreds of entries. Yeah, Live SQL is wonderful. I agree with that as well. Live SQL is great. In the past, I've done similar things with SQL Fiddle. Because in SQL Fiddle, also, you will get a URL that is timestamped. So after you submit it, you cannot change the URL, meaning you cannot go back and fix your homework. If you do, then it gives you a new link, so the old link is frozen, which is nice. But SQL Fiddle is nowhere as robust as Oracle.com, for God's sake, So Oracle is Oracle is Oracle, which means they give you that massive database support, which is now basically Oracle.com for any of us to just simply educate ourselves. So you can maintain a growing collection of cool tips and tricks that you come across in SQL. Plus, you can submit your homework through there. And I think it's pretty cool too. And you find so many tutorials, that run on Live SQL. If you Google it, you'll find them. So SQL knowledge is as simple as just clicking a few times and just jumping straight into code and then figuring out what the code does and then making some modifications. Yeah, that's a good point. We're still going through the homework answers. Yeah, that actually would be nice. At the same time, I'll just tell you, for this exercise, you actually don't need like too much feedback in the sense you're allowed to modify your initial design. So that's a big nice thing that I give you. Meaning I realized that the design that you probably had on paper might not have been the very best for these queries. So pretend that you can make changes. I said that in the description. You don't have to change it all. So it's not that it's a brand new homework. The idea is to try and reuse the table design that you had, even parts of it. Maybe keep 5 tables and redesign 5 other tables. So the point is here, this is almost like it's an independent self-standing exercise. Although in concept, it's nice if they're tied together so that you can go from a diagram all the way to queries and getting answers. Okay, so you have the flexibility to basically change whatever you want. And then anything that you assume in terms of this is not represented, this is done this way, just put that in README. That's what the README is for, because no design is expected to be perfect. In the real world, the business would beta test the database on just a few staff and few doctors, and then they'll see how it behaves and how people like it, and they might call you back for some design changes. It's never version 1.0 that is live, released to the world, so that's fine. And you've never done this before, some of you, right? So this is your first time writing SQL, so we don't expect like perfect, amazing SQL design either. Any query that works should be fine. And a tiny piece of the homework, 1 point out of 6, I guess it's not the tiny really, is just pretty much come up with your own. So I give you flexibility to have some fun with it. Just think about, if you own that business, what would you like to know? And that's a neat exercise right there. And then write the query for it, and sure enough, it works. That is what the world pays you for. So Amazon has the data on 100 million customers, right? But then Jeff Bezos does not know how to squeeze the value out of it. That is where you get, data science people come and help them extract knowledge out of it. So SQL is the same thing. I think it's a fun problem to solve. So yeah, just take it easy, do it in pieces. The main thing about live SQL is you can write small chunks. Just forget the whole question. Do just a part of it. Like ask yourself, how would I just return, what, and then add a little bit onto that. Meaning you're writing a function call in a way, and then start putting the main function together that makes all these little function calls. So do it in pieces, right? Divide and conquer like with anything else. Okay, good. And now we go back to transactions and then do distributed transactions. In a way, these both are related topics. So it's good that we're doing them together. And I didn't slide anything too much in the syllabus. I had actually a little padding. So if you notice the syllabus, it definitely is changed a little, but that's on purpose. Check this out. You short just by a couple of inches. Oh my God. See, it doesn't fit. So then issues. You definitely are probably facing some issues. And then good old Yoda comes along and it leads to bad database design. Good design, do you must. Okay, so what do we have? We've got lectures. We'll try and give you back the homework one as soon as possible, really. I think they're grading as we speak. Okay. So wonderful things are, like in the offering, this is the part that I changed, by the way, because spatial DB did not really need like 3 hours. So that's really where the padding was. Okay. Today we're going to do, like I said, this notion of multiple transactions, which is the reality for everybody in the world, whether it's eBay or Lyft, just about anything at all, buying a plane ticket. You're not the only person in the world at the time doing that thing, whatever the heck it is on the internet. And so then how can you make sure that concurrency works correctly? And then how can concurrency work correctly when your transaction is not even running on just one isolated machine? In other words, a simpler problem is, say you have Bank of America, your local branch. So then they have their own servers running like all the accounts. So thousands of people log on and they're all looking up interest rates and doing the cool things. But then you are there also logged in and you're trying to move money around. That's your own transaction. But all the transactions are running on one server at your local BFA branch. So that is, nice a problem to have, and that's been solved. But then distributed databases notches it up one more level. So now we say that there's a whole series of machines, 3 or 4 machines, all connected together using, like TCP/IP, for example. It's on the internet, some server sitting on the internet. And then when you do a transaction, parts of your transaction run on different machines. Like this one processes your invoice order. This one generates like a shipping number. This one charges your credit card. And then this one, does some historic inventory, meaning they do data warehousing. They take everything that you bought and put it in a warehouse. So these are all completely separate computers. And then the whole thing has to succeed or the whole thing has to fail. Again, it's like an atomic transaction. But now you have an atomic distributed transaction, which can have even more ways in which things can go wrong because one of those machines is broken. So then what do you do? That is what this is about, okay? So this is the smaller problem, this is a bigger problem. But in the real world, there are solutions for both these problems. It is not that we're trying to invent something brand new. We're just historically going back and filling the blanks to say, how did people come up with the solutions? So most of this is really FYI. Like big databases, don't worry about how they're going to solve all of this. It used to be a problem initially, but then it's all been solved like many times over. So we know the best practices, but it is still good to know what the terms mean. So I have to introduce some terminology and tell you, like, isolation levels, for example, and, two-phase locking. It's still cool to know how it all works, even though we take it for granted that it works. Okay, so transaction means a series of reads and writes, more than one read and one write, usually. And then involving one table or even multiple tables. And now the multiple tables can live on multiple servers all over the world. But together, the entire thing is called a transaction. And regardless of whether a transaction is one line, one table, one computer, one server, multiple servers, whatever, it doesn't matter. A transaction is a transaction is a transaction, is atomic. All of it succeeds, all of it fails. It means the problem then is if part of it succeeds, then what do you do? The answer would be throw away the part that succeeded. You can completely erase all traces of the transaction happening partly, so then it feels like it never happened at all. That is called unrolling or rolling back. So you have to roll back that partly done transaction that for some reason failed or is hanging. So today I'll tell you about deadlocks. So one of the reasons why a transaction could not complete is a part of the transaction went along just fine, but no server is broken, nothing bad happened. But the next piece of the table, some row or some column that this transaction wants, is actively being used by somebody else. But that's not a problem because eventually they're going to finish and then you're going to get it. But you might be wrong because they in turn are just still hanging there because they're actually waiting for something that you already have. So that transaction is waiting for something that you have locked, and you're waiting for something that the other transaction is locked. It'll never end. So this is a classic deadlock. So I'll show you pictures. And then a separate process has to detect the cycle and actually break the cycle. Then that means one of the transactions would have to lose and go back to the end of the queue. So there are ways to solve all of these. They're all getting very interesting. In the meanwhile, that's all a transaction is. And therefore, the transaction's job is to leave the database in a consistent state after the transaction, because before the transaction, it was in a consistent state. So the transaction should not screw up the consistency. Then it's a bad transaction, bad dog. So you want to avoid that. And so then the property that databases guarantee their owners, the users, is called the asset property. So together, they all just simply mean what I just now told you. All of them succeed or fail. And then there's always consistency that is never lost. And then even though transactions are occurring simultaneously, it actually feels like, they're all running separately, especially when it comes to writing. So when you're writing a cell, you're modifying some cell value. There's no way in heck some other transaction is also modifying the cell value. The other transaction should not even read this value, because what if you're modifying it many times? You're just aborting commit now, just keeping on modifying it many times. You're not done what you're doing. And meanwhile, others can't even read it. So you're fully isolated. That is called isolation. And then durability. So when all this goes correctly, your transaction fully succeeds. It should not be trivial to just throw it away. It should be permanently written somewhere. And then you have to go through great lengths to undo it. So that guarantees, like long-term success of the transaction. It's not trivial to just throw it away. All right, these are cool. And this is not anything separate. Usually we call it the asset guarantee, but in ACID is also this very interesting separate property called serializability. Your book has like a separate S, the letter S, but in reality it's ACID. And this means just the possibility of serialization. And serialization is the world's simplest idea. It means when 10 transactions want to all do something simultaneously, you tell all of them, line up one at a time, and you cannot all do anything in parallel. The first one completely has full control of the entire database. And when they're done, the second one has full control, and then the third, and then the fourth. So in Amazon, 10 million people would be asked to wait. So one at a time, somebody uses the whole database. That is called serial execution. It is really a fantasy because that means the whole world would be delayed. So that's not what this says. This says, even though they're interleaved, if somebody wants, mathematically, they could pull out the transactions and show in a timeline that even though they're interleaved, it is as if they're serial. Just the equivalence that theoretically it is possible to make them serial. That notion is called serializability. So when a bunch of transactions are serializable, then they are as good as serial transactions. It means they're going to be fine. So problems happen when a bunch of transactions are not serializable. That is when you draw diagrams about what each one wants. You will detect a cycle, probably detect even multiple cycles. And then that means those transactions have no chance of succeeding. And so some of them have to be broken. Okay, so that's the asset guarantee. And this notion of commit is automatically at the end of every successful translation is an automatic commit. It means it is durably written to a permanent copy of the database. A different way of saying that is all the time you're working on just a local copy of data, so that on commit, the local copy becomes a permanent copy. But the best part is if the local copy screws up, then rollback is very easy. This is not about durability, by the way. It's the opposite of durability, because you just have a local copy and you pretend you never did anything. You just go right back to where you are. You don't have to disturb the main database and say you roll back, okay? So rollback is just local. But it is possible for any reason, if you want, to actually go back and roll things back in the main tables as well. But you need the database log for that, because log is this very simple text, file that makes a record of the before and the after value. So before value got changed to an after value. So unrolling just means, throw away that after value and overwrite it with the before value. So the after is gone. That means the transaction never happened, the update never happened. All right, so then that's what this log was, and we can skip this, okay? See, in reality, every transaction ID has all these numbers, and then there's also like a row ID number, and all that the transaction is doing is it is following pointers to previous rows. In other words, a transaction will not have all of its entries serially next to each other. As time goes vertical, other transactions would be in the middle. So you need to skip past somebody else and say, I'm pointing to here, I'm pointing to here, I'm pointing to here. You point backwards and you point forwards, like a doubly linked list. That's all. Okay, but the main point about, if you ignore all of these, the main thing that is tracking is this: what was the value before? So quantity on hand was 25 units of something on your store, and somebody went and bought 2 things and they went home. So then the after value became 23. If they came back and returned the product, then the 23 can go back to 25. So you can undo it, using the log. All right, so concurrency is really what this whole thing is about, because the world is all about concurrent usage. Nobody has a database to them anymore, except on your phone. Your contact list is mostly your own database, or you have a personal recipe database or something, or people coming to your birthday party. There are tiny databases that are all yours, but anything on the public internet is concurrent, anything at all. And so then the problem is, I told you all this, and we're going to skip this. But if you're not protecting a right, then you would write something and you want that value to stick because that's the value that you computed. But then you didn't lock it, meaning you let somebody else also write about the same time. So after I wrote something, you came and wrote something else, then my changes are gone. In coding, this is a very bad thing because all the changes that I made to code are like really overwritten by your file. Therefore, we have to lock it. And then same here. So if the data is not committed, that means it's allowed to change. Some transaction is still in the middle of changing the data. It's not done yet. So in the meanwhile, you went and read something that was partially probably being changed. And so you got bad data. And then something very similar here. So you're trying to create some kind of a summation going across the table, but somebody else is actively filling inventory, they're ordering products, and so those numbers are changing. So your transaction that is doing summing up, even though it's only reading, it's going to give you a bad old value, so to speak. Again, the problem was that shouldn't happen. One of them should fully have control. The one that is doing the update should have full control. Okay, so we've gone through this, so we're not going to do it again, but 3 different errors. And all the errors have the exact same root cause, that you're not handling the mixing, you're not doing the serialization correctly. Serializability, you're not ensuring that. But in the real world, we handle it. Okay, so then lost updates, then uncommitted data, and then improper retrieval. And then there are 2 more that I told you, right? So if you want, you can go back and read about it. Yeah. So non-repeatable reads, phantom row reads. This is called phantom, by the way, because if a table update consists of not just simply changing cell values, if they consist of actually adding extra rows of data, like in your homework, you're adding more and more patients, right? So imagine you're adding patients and you added 10 patients so far, you want to add 20 more patients. Somebody went in and said, how many patients do you have in the lab today? You get the wrong number, 10. That is what a phantom row read means. Or the opposite can happen. Some transaction might be deleting data, but then you went and read it before all the deleting happened. So, so that's why it's called phantom, because the rows can actually come and go. And non-repeatable. Similar reasons, something is updating, and so every time you read, you're getting a different value because they're updating the same cell over and over many times, and they're not done. They didn't commit. Only the last value sticks, okay? The temporary values don't matter. But then you read so many temporary values, and you got so much bad data. But read up on it a little bit more than what I told you. So 5 kinds of problems, at least. There are probably more. So then the idea is ultimately you want things concurrent. You don't want people to wait, but you want it to be serializable mathematically so that it's as if they're serial. And that is what the scheduler basically guarantees. By the way, in the real world, I just want to tell you, most databases don't even run any serializability analysis, okay? This is all possible when you have probably a dozen users, 100 users. When you have millions of users, you can't even run these algorithms. So in the real world, what we actually do is use what is called timestamp-based detection. We pretty much let problems happen. Problems meaning not overwriting. Locking is always guaranteed. But when somebody's waiting endlessly on each other, that's the whole serializability problem. So we let the problem happen. And then when we notice some transactions are hanging for too long, like no update is happening, then we can do a detection and see, what is causing what to hang. And then we can kill some other transactions. We can pretty much break the cycle. That is actually what is done in the real world. But you can at any point run this algorithm on all the transactions and see if there's a cycle. Okay, so then that is called a serializable schedule if it is possible to run them, concurrently, interleaved, as if there's no deadlocks at all. Like everybody is still able to succeed independently. Okay, so therefore there are 2 broad methods, okay, using which we guarantee concurrency, using which we ensure that either there are no problems or if there are problems, we know how to fix it. The 2 techniques are lock-based techniques is one, timestamp-based techniques is the second. And of those two, timestamp-based techniques are the ones most widely used in the world. But it is nice to know about locks. Locks are very simple. So a lock is exactly what you picture a lock to be. When you go in the bathroom, you want to shut the bathroom door so somebody doesn't walk in on you. That is a lock, okay? So lock permits pretty much exclusive use of something. That's the reason why you lock it, because you want it just for yourself. So in this case, what you're locking is like a single cell value, like some row, some primary key, some column. Maybe it's your GPA or you change the major, so that update is being made. You don't want multiple people to make the same update differently. You just want one person to change it at a time at least. So then that is the lock mechanism. A pessimistic lock just simply means overlocking. So I'm going to show you different ways of locking. So it's actually going to come here, okay? I think it's one diagram. Okay, so I'll walk you through all of this. What all this means is you can overlock things. If you overlock things, worrying about transactions colliding with each other, then you're going to slow everything down. That is called pessimistic locking. So you don't do pessimistic locking. You find some optimal level of locking and you deal with it. On the other hand, completely optimistic locking, I'll tell you the very last slide, I think, is no locking at all. So what if absolutely, see, deadlock indifference, you don't even care. So what if you do that? Then that is the opposite of this optimistic locking. Come on, who cares about locking? If you want to come in, just knock. Okay. So then that's that. Usually we do something in between. So there's a process called Lock Manager, which has access to all of the locks. It keeps tabs on what transaction has, like what locked what cell. And then when the transaction finishes, the cell unlocks it, then the Lock Manager gets the lock back. So somebody's managing the whole lock business actively. That process is called Lock Manager. In the real world, that's what TRL is. In the real world, you pessimistically lock restrooms, because you assume that somebody would come in, would never leave the restrooms are unlocked, at least publicly. What the heck is RCS? I think I brought this up last time, if not, when you do software development, before Subversion, before Tortoise SVN, before GitHub, before all the modern ways of doing distributed coding came along, on a single Unix machine, there's a whole bunch of developers. And there's shared directories, user var, something, right? So then how do you check something out? Like how do you check a piece of file out for yourself and then put it back in? There are two mechanisms in Unix, do you know? One of them is RCS. So maybe at least I'll ask you, what does RCS stand for? What is the other one called? There's two locking mechanisms that are very popular in Unix among small developers. If you're a little developer, you don't need GitHub. Okay, you can do it locally. But there's two of them. Yeah, exactly. CVS, wonderful. Like your drugstore. CVS is called concurrent version system. So CVS is optimistic locking. Okay, so you can check something out for yourself. A lock is placed, but so can somebody else. It just keeps tabs. How many people check something out. But then it is up to all the people that checked it out at the same time to merge their differences. Otherwise, one of them is going to override the other. But the system will happily hand out multiple locks, multiple write locks. It's weird. That is called CVS. RCS is not like CVS. It is much, much more strict. It's pessimistic locking. So what does RCS stand for? CG, do you know? C stands for control, something control system. When you're doing coding, you're changing the file all the time. So what is change called? You are modifying, yeah, exactly, revision, wonderful. So RCS is a revision control system. Okay, read about it if you want. This one person gets a lock to a file and that's it. So others have to wait, the whole studio, the whole department, the whole unit has to wait until the one person checks that file back in and then somebody else can get lock. One at a time, pretty much. What is Robert's Rules of Order? When you go to a public meeting, so there's a pretty heated debate about your city's vaccination schedule. People are pretty pissed off. They want to get back to work and blah, blah, right? So then it's a pretty contentious, angry meeting, people yelling at the city hall, mayors and everybody else, board, the city government board. In there, you would use something called Robert's Rules of Order. Very simply, what does it guarantee? Anybody know? Sounds like an old parliamentarian procedure. Robert's Rules of Order. Many organizations, by the way, seriously follow this. Is a big deal. Okay, so just simply in 3 words, one person speaks. Yeah, taking turns, exactly. Oh, I like that. Even better, 2 words. I love it. Yeah, taking turns to speak. That's exactly what it is, okay? So if you have a minority opinion, it means even your single small little voice will be heard. No one is going to talk over you. Nobody's drown you out by the shouts. When it is your turn to speak, no one else speaks. Yeah, it's almost like a stick or a piece of like napkin or something you pass around. Whoever holds it literally, they are the ones empowered to talk by the whole system. If you disrupt it, you can be thrown out, okay, because people agree to that rules. But same idea, okay? You're locking basically the I guess privilege of talking. It's given to one person at a time. It's very neat, okay, look it up. It's to protect the little guy, so to speak, of course. Okay, so lock granularity. If you go overboard with locking, because some transaction wants locks, then you would slow everybody. So the level at which you can lock for a transaction, something is called lock granularity. This means how fine-grained. Fine-grained means very small detail, and the large grain means big picture. Okay, so the granularity can be in like one of these, like 5 different levels, okay? And they go from pretty pessimistic to, fairly optimistic. And so you pick the middle. You literally pick page level locking. Okay, I'll tell you what it is right here, and then we can easily scroll through all of this. Pretty simple. A database level lock is exactly what you think it is. A database, by the way, is multiple tables. So in your homework, all your tables together, the entire dental business database is called a database. So imagine somebody wants to make one small change. The front staff person scheduled a new visit for a patient. And so they just want to go in the schedule and add the patient's name. In the meanwhile, imagine locking the entire database. So somebody cannot even order inventory, just something entirely separate. Or a surgeon cannot update their credentials. They just got the certification renewed. Then they're not able to log in. That is what database lock means. So any change anywhere in any piece of the database would cause the entire database to be locked and given to them. So it is pretty crazy, right? You don't want to do that. A table level lock is exactly what it says. So only the one table, even though there might be hundreds of rows and you're only trying to modify one little row, the whole table is locked so that nobody else at the time can log onto the table. They can use that table. They can use other tables, but no transaction can run on the entire table. So you lock the whole table. That's also too much, because you don't really want that. Say Amazon did this, to the product catalog. It means each person in the world is buying from Amazon one thing one at a time. Completely untenable. It's unworkable. A page is a piece of a table, like an operating system's page. So a table these days can be quite large. So a page can be like a certain chunk of memory, like 2 megs worth of rows, or 16 megs worth of rows. So then that page, there are independent pages. The table is broken up into multiple pages. So then your transaction happens to need some row that falls within a certain page. It means only that page would be locked. All the other pages still in that table would be available. So others can read and write, but nobody can do things in your page. But sometimes that can be a problem, right? Because if somebody else wants a second, the row right next to your row, it just happens to fall in the page that you have. The page locking will lock them out. But instead, something even more fine-grained, so row level lock. This makes a lot of sense because only the one row that you want to change, only the one student, the one product, the one library book, the one just one, that would be locked for you, and that's quite cool. But this is even more extreme. It means even in the student table, somebody could be modifying, your graduation date, and then somebody else can be modifying your GPA because they're independently locked. That is called field level lock. This is way too much work to track the locking, these two. And this is way too, serious, meaning it locks people out. So this is the happy medium, Goldilocks. Hey. Yeah, so that's very cool. The tree protocol. Yeah, so how do you know about tree protocol? To work in databases. Okay, I'm going to keep going. Yeah, so, please look that up. That's very cool. I like when people put up, terminology, right? If you want, you can Google it, but I'm going to show it to you. So here, the whole database is locked. So imagine database only has 2 tables, okay? Time is going vertical. So it means transaction 1, maybe my transaction says, I want to lock the whole database. And then at time equal to 2, it says, okay, you have a lock. So during that time, between time equal to 2, 3, 4, 5, 6, nobody else, such as 2, can also get access to that same database. Maybe I'm only modifying it here, right? And maybe 2 wants to change here, but 2 cannot do it. 2 has to wait until I'm done, and then 2 is able to lock. Conversely, when 2 is doing its thing, I cannot come back and say, oh, I forgot to change one little thing. I have to wait. So it's making the entire database locked, okay? Okay, that's too much. A table level lock is the same diagram, but now imagine this is zoomed in. So you're only having the whole table fill it out. Again, I'm not going to repeat it. The whole table, so somebody locks it, somebody else has to wait. Instead of 1, by the way, imagine hundreds waiting, okay? It's the same idea. And then a page level lock is a page is simply a part of a table. So Like here, it says a table has been broken up into 2 pages. So someone can only get a lock for just the one page where the row or rows happen to be, and then others can happily keep working on a different page. I think that's a very good compromise. On the other hand, a transaction can just request a lock for just only one row, just exactly row 1. In the meanwhile, some other transaction can get all the other rows. And this transaction for the time period can only lock that second row and all the others available to everybody else. Okay, that's, oh wait, sorry. I will. Yeah, oh, I was going the other way. Yeah, definitely. Over zoomed. Glad you asked. Okay, so this is the main one that matters, but just for the record, okay, I'm going to put it all up because it's being recorded, so might as well record it nicely. All right, so database locking, that's clear, right? And likewise, a table locking is the same as a database locking, but the diagram is now for just one table, and then the whole table is locked, even if you only want a few rows. And then this is the middle ground, where the table is only locked for a page, not the whole table. Yeah, field means one cell. Field is literally just one little square, okay? Because row means all the cells. So if I lock a row for you, if I lock row number 4 for you, and then you only modify somebody's last name, somebody else wants to modify something else, your advisor's name, they won't be able to do it because the row is locked. Cell lock means if I want to modify the last name, I'll only get a lock just for that one column, and then somebody else can then access some other column. So it is the finest level of granularity. So we've gone from the smallest level that you can lock, which is one cell. It's too much overhead, and it's basically unnecessary, versus locking the entire database and making everybody wait. So those are the two extremes. That's why the page locking seems like a good thing to follow. In many implementations, if they do locking, that's exactly what they do. Clear, right? It's all depending on usage, by the usage cases. If the usage, in some places, so that doesn't matter about all the tables, practically almost all the time. Everybody is working on just a few rows all the time. So then field level locking makes a lot of sense. You shouldn't even lock rows, you should lock fields. It just depends on what users do with your data. There's no one answer. But the nice thing is the system allows you to do anything that is reasonable. Okay, so that's all, okay? I don't even have a field example, but imagine this one little cell is locked for you. At the same time, others can lock different cells in the same row, or the same page, obviously, or the same table, or the same database. Yeah, because you only have that one cell, because that is all you're writing at one time. You cannot concurrently write multiple things, right? So you assume this ordering. All right, so moving on then, locking types. So then, this whole notion of locking, it's a very simple version called a binary lock, which we don't do in the real world because it's not very useful. But instead, we do this notion of exclusive versus shared. A binary lock just means, well, let me back up and tell you, there are only 2 operations ever that ultimately happen in any database. So it's all about just the 2 operations. The 2 operations are simply reading, writing, and down to one cell actually, because it all comes down to a cell. So you're either reading a cell or you're writing to a cell. And so I'll start by saying that's what this is. When you're writing to a cell, no one else can write to that cell, because obviously otherwise you're going to overwrite each of these values. So a write lock is also called an exclusive lock, or an exclusive lock is granted to a writing transaction. That is the only time it has to be exclusive, because only one transaction writes at a time, right? That's how you prevent overwriting. Okay, the very first example I started with, that one happened if you exclusively lock one and then the other one comes along, can do whatever it wants. At least there are 2 different transactions. Okay, so then that is exclusive. On the other hand, if you have a cell like Amazon textbook price or laptop price, and so many people are just browsing, it's basically, I don't know, open season for buying stuff. You're locked at home in the pandemic and you want to go shopping. So you just scroll, just look at stuff all the time. So when Amazon shows you catalog items after catalog items, people just click on it, but they're not even buying. They're just looking, look but don't touch. That is called a shared lock. Because if all that is happening is reading, no other transaction is writing anything, there's no possibility of anything changing. You can have what is called a shared lock, which is all reads. So reads can be shared by as many transactions who want to read, because you're not literally modifying the value. It makes sense, right? Okay. So then there's a third state when there's neither happening. So some cell is completely free, nobody's doing anything. And then one of these can come along and get access and be given a write lock or read lock. Say there's a cell here that is completely open. A write lock comes and says, I want to write. Then that cell would be given a write lock to for our transaction. And while the writing takes some time, Some other transaction says, can I read? No, you have to wait. So that is the exclusive. On the other hand, one second, okay. On the other hand, when a transaction is completely free again, like I said, or someone wants to read, then they're given a read lock. By the way, reading even needs to be locked, because if reading is not locked, then somebody might accidentally be given a write lock. So it has to be locked somewhere. So reading lock is fine. So you got a reading lock, you're reading it. Somebody else comes and says, can I also read? Sure, you can also have the same lock. That is why shared lock. Okay, so reading can be shared. So you go from an unlocked state to a reading state. I think I drew this diagram last time. So unlock to lock, unlock to read, and then multiple reads. You can loop in reads. When you're done, you go back. Likewise, unlock to write. When you're done, you go back. So always put it back, whether you finish reading or writing, just give the lock back. Lock manager handles it all. You don't directly pass locks around, okay? So a transaction will not give its read lock to some other write lock. It's not his business. It just simply surrenders the lock. It all makes sense. What is the field level lock? So CG answered it. That is correct. Okay, yeah. Okay, good. I like CG's practical answer. That's why I teach with examples. Okay, so lock types are very similar. Yeah, the binary lock then. So this one doesn't care whether you're reading or writing, okay? So this is two states called locked, unlocked. So it's not very useful because we don't have to waste the binary lock for multiple, this. So this does not even care that somebody's reading or writing. So we don't use binary in the real world. We actually use this notion of exclusive versus shared. That is why it says here, using that concept, there are three states, unlocked, and then shared read, and then exclusive write. Everything starts out life as unlocked, and then you can get a write lock, and then you give it back to unlocked, meaning put it back to the lock manager. And then when you come back, then you can be given, somebody else can be given a read lock. And then someone else can also be given multiple read locks. And then when they're all done, you go back to being unlocked. And then one of these can happen again. It's just a very simple little state diagram. Okay. So three lock states. All right, so again, just more ways of saying the same thing. So read is always shared, write is always exclusive. I mean, again, from a coding point of view, this makes sense. That's why in GitHub, you have all these repos with thousands of files. And then you're allowed to just check out anything you want. Just pull down the repository, make any change you want. But you don't get to just copy your change. You have to send a request to the maintainers and say, pull my change and see if it is good. So that is their way of guaranteeing that multiple people just don't override each other. If the repo owner, decides to throw your change away, then they don't have to actually accept your change. All right, so that is the notion of, pull request. You send the pull request, then they can accept it. They can manually merge it if they need to. There might be incompatible changes. You might have done like change one way, some other developer did a change in a different way, and only one of them is correct. So you cannot even merge them. You have to basically override one by the other. But it's not automatically done. That's the point, okay? So some human has to do it. All right, so shared is read. So, and again, shared can happen only from an unlocked state. You always start from an unlocked state. And then, or from read state, actually, sorry. So, again, if you're already reading, somebody else can get read lock. So reads can be all shared. On the other hand, this can only happen from an unlocked state. In other words, you don't want all of a sudden lock something when other people are reading it. Because then when the reading process continues, you're starting to modify the value. Then you start to get, inconsistent retrievals for the others. Okay, this all makes sense, right? So exclusively, you can only go from an unlocked state like this. See, literally canvas. Why not? Just for formality's sake, I'll just do that, okay? Okay, so here's an unlocked state. An unlocked state. So unlocked state, a read lock can be given. And then if a different read lock is required, it's okay for you to be in the read state. So then that can be done as well, meaning more reads can happen. On the other hand, if somebody wants a write lock, it can only be given to them from an unlocked state. And then when they're done, then they surrender the lock. Likewise here, when they're done, they surrender the lock. This cannot happen. You don't pass locks back and forth. Okay, so then that is locking. But what do you do with the locks? You do a very cool algorithm called two-phase locking. All right, so this is a pretty practical, wonderful algorithm. And some databases, for example, MySQL, does implement a version of this. In fact, not the version that I'm going to tell you. So I'll save the version for the discussion, okay? But I'll tell you the basic, like with the two-phase locking algorithm. It's cool. You can think about it. And then we can try and make it like more serious and see what the ramifications are. All right, so two-phase locking. First of all, if it were up to me, I would call it three-phase locking because it's actually three phases. but then they leave out the middle phase, which is weird. This is time. It's time. Easy. This is, I guess, number of locks acquired, because it's going to go up monotonically. I guess I'll just say number of locks or something. In reality, this actually doesn't make any sense. Okay, you're just drawing a diagram over time. The idea is this. So you have a transaction T, and you have all these tables and cells like all over the place. There's so many rows and so many columns like in your homework. So this transaction wants to make some change here, and afterwards make the change over here, then make some change, whatever. Some changes are right changes, some changes are read changes. In any case, they want locks. So some transaction T wants all these locks. Meanwhile, some other transaction, maybe call it Q. Maybe it wants like that cell, and then wants that cell, and actually wants that cell as well. And then wants that cell, in some random order, right? Meaning whatever the order, that transaction wants. But the idea is transactions want locks all the time. This notion of a two-phase locking algorithm, which I would call three-phase locking algorithm, proceeds like this. The actual transaction, which is all the reads and writes, cannot happen until that transaction is true for this and also true for this, simultaneously, meaning they have nothing to do with each other. Any one of them can start. In reality, thousands of them can start only after all of the lock acquisition succeeds. Say I want 4 locks. I got 1 lock, after a while I got the 2nd lock, then I got a 3rd lock, then I got a 4th lock. Monotonically, my lock count is going up to how many locks I want. Once I get all the locks, then the system basically tells this transaction, go do your thing. And then the transaction does calculations. This is where the real stuff happens, the reads and writes, right? I'm moving some money around, I'm merging tables, God knows what I'm doing. But then when I'm done, I can then release all the locks back to the lock manager like this. That also takes time, right? You release them one at a time, I believe. It's called 2PL. For now, we'll just call this 2PL. So then this is exactly what it looks like. This is the so-called growth phase in time. This much time is taken for the lock growth to happen, for all the locks to be acquired, all of them. And then this is the time it takes for the actual transactions to happen. And this is the time that it takes for all the locks to be unlocked, and your transaction is 100% done. So the nice thing is this: if we're able to get to the top of the pyramid before we get to the top, meaning we're almost like if we're over here, meaning if you get all these locks, then this transaction will succeed no matter what. Even God cannot stop this transaction from succeeding. God says, oh yeah, hold my beer. I said, no, God, you can't do it. I'll challenge God. It's funny, God laughs at me. Watch. Poof, city vanishes. Okay, so therefore, this is basically ironclad, right? Because what can possibly stop this transaction? A lot of times transactions get stopped in the middle when they, go and change this, and then they go and change this. Next, they want to change this. Somebody already has locked it. So they just wait. But in the meanwhile, whoever locked this, made this change, and then they're waiting for you. So this is why it'll never end, okay? So you're waiting for them, and they're waiting for you. This is called the deadly embrace. There's your deadlock right there. Okay, so that possibility can never happen here at all, because no matter what, don't care about others. Anything that you need, if it's what you need, the lock manager already gave you this, so you will not wait for somebody else. That is wonderful. That is why I told you, once you reach this stage, free run the whole place. By whole place, I mean just your locks that you want, and then undo it and be on your way. That is called two-phase locking, because there's a growth phase and a shrink phase for the locks. But I call it three-phase because there's a growth phase, a transaction, actual happening phase, and then a shrinking phase. Okay, think about this, okay? It's a neat algorithm, all right? And it works. What does it do? It says, defines how transactions acquired, relinquish means give back. So how do you give it back? In real life, if someone has a right lock on something, other people, yeah, they are. They absolutely are. Yeah, Amazon, actually puts up with temporary inconsistency, okay? In the worst case, they'll sell you a book that they don't have, and then they'll apologize. That's really what happens. Or in the worst case, say somebody's changing the price, the product manager puts things on sale. They'll sell you the book at the full price, and then refund the rest of your money. Yeah, so they don't care. This actually called a base. I might as well tell you. Base means basically available. That's what it means. It means no locks almost. Soft eventual. It means the consistency, the problem that happens with the overriding can all be fixed later on. So because chemistry, right, acid, base. So base NoSQL, the world of internet, prefers customers not being lost. In other words, you don't let people wait because people will go away. So you're 100% right. they let problems happen and then they go and fix it. Yeah, cool, good. Except in some critical cases, airlines will definitely lock because you don't want to sell the same seat to 20 people, then there'll be 19 angry people, right? Yeah, why the deadlock will not happen? Okay, that's a nuanced question and a nuanced answer. That means, actually, I didn't say that, but I said that. In fact, here's what I said. Good question, Deep. Let's go here. Pick a different color. This is fun, by the way. Okay, this is where the thinking comes in, and you go, wow, this is a neat algorithm. I'll tell you why. Okay. All right. So then this is the release part of it. Again, just take some very simple cases like this. So I want a lock here and I want a lock here. So then my transaction's name is A. So I want both these locks. And then some other transaction is B. And then, they have this lock. Then maybe B also has this lock. And then, so then after I want 3 locks really. So I want this lock, and also I want this lock. So I'm going to put it in parentheses. Likewise, B also wants 3 locks. It wants that one, it wants that one. And then it also wants this one. No lock has been given yet, by the way. Okay, they're all completely free. What the lock manager starts to do is it's serving everybody simultaneously, not one at a time. So the lock manager gives me this lock. Lock manager gives me this lock. Simultaneously, the lock manager also gave the other transaction this lock, gave the other transaction this lock. Now the lock manager says, so what does this A want? A wants that one. Oh no, we can't do that because B is in the middle of completing. What does this B want? B wants this one. Well, B cannot be allowed to proceed because A has that. You see? So they both are given partial locks that the other wants, and then the system is stuck. Okay, suppose you get past this. Okay, in other words, suppose somehow you are able to get this lock for yourself. Say A has all the 3 locks. That is when you're here. So in my example here, you had 1, you had 2, and then you had 3. Then you're here. So once you get the locks that you want, then you can fully operate deadlock free. There's no deadlocks at all. You got all 3 of them. Just do whatever you want, and then you're done. So then there's something very interesting about this. What is it? So what's the deal here? What comment can you make? Like, what can you say about this? Like, what could have happened? Like in this case, suppose take the real world, right? This lock is that lock. Okay, so this means that lock was given to you. This means this lock was given to you. But now we're not able to get this third part because there's a different graph somewhere very similarly for B. B all exactly. So I think you have the right answer. I'm gonna read it. So B also was given like that lock. So B was given that lock, and then B was given this lock. But then now B cannot be given the third lock. So this is stuck, and also this is stuck. Can you explain why the deadlock will not happen? Exactly. So this is perfect. After the growing phase, deadlock is guaranteed to not happen. So Deep has the right answer. That is what's magical about this. Okay. So after all the locks are acquired, deadlock cannot happen. But that means deadlock can happen. I just showed you. Deadlock can absolutely happen in the growing phase. That's very interesting. Okay. Yeah. And then when that happens, the system will unroll one of them. It'll basically take A's lock that's being A is holding, right? So push A back to the end of the queue and give that lock to B. So then B is allowed to fully proceed, and then B will release all those 3 locks, right? And then at some point, hopefully, A will get them. I'm saying hopefully because when A goes back to the end of the queue, there's a whole line for all these transactions. So when something is, say you're at the head of the line, when you're unrolled, a part of you, is gone, then you will go back to the back of the line. It's very hard to insert things in the middle. Okay, a queue is like a standard data structure. So we don't find some way to insert it. Although you can use timestamps, and then at least give it a little bit like in front of the line. But in general, just say that you go in the back of the line. And hopefully when you come back, the same problem won't happen again. There's no guarantee at all in the growth phase that deadlocks will not happen. It can, okay? But the guarantee is after. Clear? Good. Okay, then we unlock. Again in pieces, okay? Remember that part. It's still unlocking in pieces, meaning it takes time to unlock. All right, I'm gonna read. During the growing phase, transaction acquires all required locks without unlocking any. Yeah, so this is a strict monotonic scheme. Monotonic lock acquisition, and then the transaction, only then the transaction. Monotonic unlocking. What that means is, suppose, this is just simply like a write. Just because you got this one lock for writing, the transaction is not allowed to just go and make that write. It's got to completely wait, okay? In other words, say what I said is not true. You can, even before all this happens, I can get that lock, and while I'm waiting for these, unlock it. That is never part of 2PL. So in 2PL, you cannot unlock before all the locks are acquired. It's almost like curly braces, okay? In programming, you're only allowed to have all the left curly braces, and then do your thing, and then only then you're allowed to have all the right curly braces. You cannot do like in a stack programming where you can say push, push, and then pop, push again, pop again, push, 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 pop, 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 pop. That is possible in programming, but then in two-phase locking, that is not allowed. Okay, it's only strictly all the left curly braces followed by strictly all the right curly braces. Think of it like that. So if A and B are fighting over locks, will it take a lock? Oh, yes, absolutely, sure. So Molly is correct. That is what I meant by unrolling. Okay, so the lock manager knows that this is happening, and then one of them, the locks that were given to it, will be put back in the system. And then if one of them is wanted by the other one, then that'll get all the locks that it wants. Yes, correct. Cool, Molly. All right, so then that is what happens. Therefore, there's no guarantee while growing, but after finishing growing, there's guarantee of no deadlock. So shrinking is when you give the lock back. All right, so the 2PL type that we're discussing, where a transaction acquires all the locks it needs before processing starts, is called conservative 2PL, static 2PL. You can just start to Google these, all kinds of fascinating discussions come up. People go in Stack Overflow. I don't understand. So then, all this Gate Overflow, .India, Geeks for Geeks. I mean, there's lots of articles you can read, but these days it is a solved problem. So read it just for fun. In interviews, these things do come up. Like the things you're asking absolutely come up because people want to know that you understand. Okay, so there's a lot here. See Stack Overflow. What is the benefit? And they'll tell you. Database administrators go and answer all of these. For now, we'll just call our scheme where it had a growing phase, almost like a Mayan pyramid, okay? The pyramid steps, the flat top, and then pyramid. Why Mayan pyramid? Why not? Oh, come on. Today we got like a lot of time. Not the Egyptian pyramid, but the Mayan pyramid with a flat top. That's the difference. It's a truncated pyramid. Computer graphics. It's the view volume. It's that. Growing phase, transaction phase, shrinking phase. An Egyptian pyramid, on the other hand, goes all the way up to the sharp peak, the vertex there. Okay, that's what we talk about. Look, it even matches. OMG. All right, so once we get there, you're home free, okay? Now, more about this. So the whole point is, this is all doing the, governing rules means why are we trying to do this? Because what you don't want is at the top, meaning when a transaction is partly done, it discovers all of a sudden, wow, I wasted my time doing all these transactions. Because look how cool this is. At this point, no transaction actually happened. Imagine these calculations taking hours or minutes to finish, right? None of that happened here. See, if the system already detects that while two of them are growing, there's a deadlock between them. One of them is gone. See, avoid all the processing time. Suppose you don't do any two-phase locking at all. Then the opposite happens, meaning you don't have any of this. Transaction one takes a long time to update this cell. Takes an even longer time to update this cell. And then it is stuck updating this cell because it cannot get it. Likewise, B spent a hell of a lot of time doing this, and then it's not able to get that. That situation will never happen in two-phase locking. Okay, that is the governing rule. We don't want to waste computation for no reason, meaning we should not have deadlocks happen after transactions start to occur. So you try to prevent the deadlocks, try to avoid it, try to kill it before transaction, even actually calculation start to happen. That's the governing rule. You cannot have conflicting locks. And also this notion of no unlock and proceed before lock. This again is to guarantee that you just wait to do all your transaction as a block, like a serial execution really. And then, and see, this just means no transaction really happens. No reads, no writes, nothing. Just wait till you get all your locks. Okay, so far all your questions are answered. Once all the locks are acquired, then you can proceed smoothly. So it won't hang. So hang mean wait for somebody else. That is not possible because by definition, you already have your locks. Lead to dirty writes means while you're writing, somebody else is not going to read it because you have the exclusive write lock for yourself. So others cannot, have a dirty read happen to them. Problems are prevented easily. And then this is the example that I gave you. A loose analogy is programming. This is really what two-phase locking looks like. Whereas in programming, you can clearly do pushes and pops, right? You can have a little block, this if statement, this another for loop, whatever. So that's pretty simple. But we don't do all of that. We assume that all the left curly braces only, then all the right curly braces. The middle is your transaction. Wow. If you do 3 of them, you do volume processing. In graphics, you take 3D data. Minecraft, you can render Minecraft this way. Okay, so then you have that's clear. Then what else? Does commit work instead of unlocking? You know, those two are highly related. Hold on to that thought. It's a very neat thought. They're two different things actually. And those two different things interact, which is why the strict two-phase locking is not the only game in town. Okay, so hold on to that thought. We'll come back to that thought. You know how we called it conservative two-phase locking. There are others, okay? There are others. And why there are others is because of exactly this. There's actually some kind of a link between committing and unlocking. Not even committing. Think about aborting. Aborting can also happen. Okay? So at that point, you can either commit or you can actually abort. And both of those somehow, screw up other transactions. So you can start thinking if you want. But yes, definitely, this is a cool question. It's a neat answer. We'll get there. In the meanwhile, just a little picture. The time is here. So this is just for one transaction. It acquires a lock. So the purple thing is a lock. Acquired a second lock, acquired a third lock. After 3 locks, it got everything that it wanted. And then it can do its transaction again. The middle part is the most important part. They just call it operations. This is the reason why you did all this in the first place. I would make it wide if I wrote this textbook. Make it wide and then make it small. And then you release. Not necessarily in the order, by the way. They should have colored it differently. There's no expectation that it's not a stack or anything, okay? So you don't need to release this first, release the second. This can be in any order. Is 2PL efficient? Oh, yeah. So this is a private question. One transaction potentially have to wait a long time. I mean, there's no other option, in the sense, what is more, inefficient is if you let transactions happen. And like I told you, they partly change all kinds of tables. Like say Amazon, right, starts to ship, accept the order. They've already sent to all the robotic, workers in all the warehouses, your line items. So you're going to be shipped from like 3 or 4 different places. They got a tracking number, they got this, what. And finally, they discover that your card number is bogus. It expired last year. You didn't renew it. It's bad, right? So therefore, this is a hypothetical toy example. So I guess what I'm saying is it is easier to look for locks and, give them or grant them or not give them, rather than having a transaction partly occur, than having to unlock that, unroll that back. So that is how I would answer it. Locks really are an easy mechanism because locks don't take as much time as the processing actually. And the lock managers constantly watch for all these cycles, they run the cycle algorithm at some interval. And so nobody's really going to hang for too long, it finds out. And then it kills one of the transactions. It usually kills the younger one. There are timestamps. It makes sense that, something that's newer can just go back and wait. Something that's older, probably should get all the locks. But that's not even the only scheme, by the way. There are other schemes. In the meanwhile, two-phase locking. Simple, very simple. Okay, so this is now, it makes a lot of sense. A deadlock is, again, when 2 transactions wait for each other. Or you have this classic dining philosopher's problem, when you can have many transactions and they can all wait for each other like in a circle, and then nobody will get what they want. So 100 transactions potentially can even wait for each other, all of them. And so then that is called the dining philosopher's problem. And I can draw a simple little picture because philosophers are starting to have dinner. And then each philosopher has 2 forks. And the idea would be you have to pick one fork first, then you got to pick the next fork. And when you have both forks in your hand, you can start eating. Everybody has left fork and right fork. So the rule says all of you pick up your left fork and then wait for the right fork and then you can start eating. So everybody would pick up the left fork and guess what? This person's left fork was like, by the way, there's only one fork in the middle. So this was that left, right, they picked up and you are never going to get it because, they're holding on it. Likewise, they'll never get the right because they picked it up. You literally go in a circle, you are stuck. Dining philosophers. So in other words, this whole deadlock idea is not just 2 of them back and forth. It can be extended to any n number of transactions, and it's 2 in the smallest value. When you lock the first resource, the second resource is locked by a transaction. How does it deal? When you lock the first resource, but the second, yeah, right. So it has to undo one of them. So that's exactly it. Okay. So say you lock the first resource. This first resource is locked by me. That's for me. And then there's another resource is locked by somebody else. Okay. Except now I want that. So the lock manager gave me this lock. So here's a T, and then I have one lock. So that's me. And this is the other transactions. Let's call the transaction B, right? And so then B got the lock that they wanted, this B, right? So now I want this one. I want this one. But the B should also be allowed to succeed, right? So then the lock manager looks and says, wow, what else does B want? So B wants A, right? So B can never be given this lock because I already have it. Likewise, I'll never be given this lock because B has it. So we both cannot get to the next step, right? So then you deal with the problem by killing one of them and saying, forget this belongs to B, give it to A, so let me do my work. And afterwards, B can come back and say, can I have this? Sorry, I guess that one. Can I have this? And then the lock manager says, yes, cities, then you can have it. So the way you deal with the problem is you unroll one of the two or one of the many transactions that are waiting on each other. Cool. Yeah, so in this case, you just kill one, definitely. You don't have to kill both, just kill one. There are all kinds of metrics you can use. You can kill the one that has been given the least number of locks. Suppose I have 5 locks given to me, and then you only have 2 locks given to you. It makes sense to kill you, right? And so that I can succeed. Stuff like that. Or say I'm older, I've been waiting for a long time, and then your timestamps are younger, then maybe you should be killed. Stuff like that. It's practical, ways to kill. If you kill just one, no need to kill both. Cool. So these are fun. Okay, deadly embrace, they're all like trying to kill each other. So when you have deadlocks, because deadlocks are just a fact of life, you can know this notion of prevention. I'll actually magnify this. So prevention is you try to make sure that deadlock, just does not happen at all. This slight difference between preventing and avoiding. So I'll explain the difference. Detection is you don't care about deadlocks. Once in a while, you see if deadlocks happen. You run like a cycle algorithm. And then if you see a deadlock, then kill one of them. That's called detection, okay? But then prevention and avoidance, I'll tell you. And then, so you can pick any of them really, and they all work. And it depends on, what the DBA wants, what the users want. Different strategies. Okay, so then what are the differences? I want to read them so that we get it right. So prevention versus avoidance, because they sound like the same, right? I want to avoid getting the COVID-19. I want to prevent getting COVID-19. Sounds almost the same. But prevention is this: a transaction, a new lock, when there's a possibility that a deadlock can occur. So this is where you were just asking this. So when you do deadlock prevention, you always look for something that is wanting a lock. And then if there's a possibility that a deadlock can happen, then you simply abort it. You try to, so that way that transaction can never even have the chance. You're just aborting it even when it's asking for the lock. This one is what we're doing with the two-phase locking. You're saying avoiding because you must get all the locks before it can be executed, because you're trying to avoid the deadlock from happening while the transaction is happening. So then that's avoiding. But this means while the locks are being acquired, there can be a possibility that the deadlock can happen. And at that point, you're doing prevention because you're trying to kill one of them that can cause like a deadlock. That's all. Okay. So avoiding, in other words, goes with the two-phase locking after all the locks are acquired. Transaction must obtain all the locks, and then when it's rolling back, while the transaction is happening, you don't need to roll back anything at all because by definition, you got all the locks that you wanted. Cool. And so then like you guys were asking, it is inefficient because, at the growth stage, you have to wait for as long as it takes because that is a rule. You cannot start until you get all the locks. So at that point, the reason why you wait is because, maybe somebody else has it and then they need to be unrolled and then it takes time. So then you're trying to prevent. Okay, so just think about them a little bit more. 607, a little bit more time. Yeah, right. So then this notion of, preventing deadlocks, again, timestamp based. So I told you, when two of them are trying to deadlock in the growth phase, you can use timestamping to see who should be killed. I have another slide coming up, I'll show it to you. So you can use timestamping to, like prevent deadlocks in the sense, unroll one of them, kill them. And then two-phase locking, once you get to all the growth stage, at the top of the growth stage, avoids deadlocks because there's no possibility. And then detection, so cycle detection is what you would do. When I say both, we don't need to actually do it for this avoiding, for two-phase locking, but you will do cycle detection to see why these locks are not being fully, going all the way to the top. Okay, so that is timestamps. So timestamps are the next thing that I have to tell you. So how one way deadlock? Okay, this is a very easy slide, right? Again, time goes vertical, only two transactions, A and B. This already drew you many pictures. You can look at it. So at time 1, transaction 1 gets X. So X and Y are 2 cells, okay? 2 database cells, 2 table cells. So I'm T1, I got X. But now next, I want Y. But meanwhile, in between my getting Y, then I'd be happy if I got X and Y. Somebody else came along and said, I want Y. So then they got Y. After that, I'm saying, can you give me Y? System says, no, you have to wait. Meanwhile, the other one that got the Y says, can I have X? No, Sati has X. So they can just endlessly wait. This is when many processes, have timeouts, meaning many database, systems look for a certain amount of time when no state changes happen on a transaction at all, meaning there's nothing happening. They're just hanging. And then you can run a cycle to see what is going on. In this case, T1 is literally pointing to T2 and says, I want Y. T2 is pointing to T1 and says, I want X. So then that cycle should be broken. Cool. In this case, we'd probably break the cycle by killing T2 because T1 is historically earlier and T2 is later. So that's what you do. Or so, yeah, I'll just say that. Okay, so then that's how you create the deadlock. And the same thing can be said in many ways. Okay, you can read this. So T1 locks X, then T2 locks Y, and then, but after that, T1 wants Y, and you cannot get it. Meanwhile, T2 wants X. Cannot. So each one got half of what they wanted, and then the other one has the half of what they want. And then you're stuck. All right. So that is why you cannot just release what they're holding. In other words, T1 cannot just simply release X because that means T1 is aborting. T1 wants to succeed. It can succeed only if it also gets Y. But in the meanwhile, somebody got Y, and they can succeed only if they also get X. So each one of you has the other half. One of you has to yield, right? Literally fighting in the middle of the road. You go first. No, you go first. You yield. No, you yield. So one of you has to yield. In a one way, like a narrow bridge or something, right? That's basically what happens, believe it or not. So when two cars drive literally down the middle, and then each one refuses to give up, you cannot go home. Okay. What is actually this one? So it's all the same, it's saying the same thing. Suppose it's a long stretch of one-way road. Usually there are, red lights that say, so only one car can pass the whole stretch because it's very thin. If the light is green, and the car actually is supposed to go, and the light will only, turn right after the car fully passes, okay? Meaning somebody else will get a green. But suppose that it's red here. You don't care. You think, oh, come on, there's probably nobody coming, right? When you start to just drive. But sadly, it's red here because somebody had a green and they start to drive. You're literally stuck in the middle. You cannot pass each other, by the way. It's such a narrow bridge, narrow road. One of you has to basically back out all the way. Okay? Probably pretty hard. Yeah, so this happens in real life. In Palm Springs, by the way. So if you go to Palm Springs, Joshua Tree, actually. Joshua Tree. One of the exits to Joshua Tree, I think the eastern side exit, has a very long stretch that is exactly that. So if you ever go there, if you're leaving the park, it is red, no matter how long it takes to stay there. Otherwise, you'll be stuck in the middle. Okay, so one has to yield is the problem, okay? Because each one has the other half of the road that they want. Oh, yeah, so then like this, before you release, there's no releasing, okay? You have to go all the way, but you can't. And that's true for both of them, and then deadlock. And this is the notion of circular waiting, dining philosophers. Two really famous computer scientists, Dijkstra and Hoare, they both got, the Turing Award, okay, for computing. They talked a lot about concurrent processes, both of them pretty amazing. Read them up. But they talked about both the whole dining philosopher. So here it is, okay? So the rule says you can start eating by first picking up your left fork and then your right fork. Go. Everyone picked up their left fork. And then they never put it down because there's no right fork, right? Then everybody's stuck. Okay, read. All kinds of solutions, but philosophically there's no solution. I mean, something has to give. There's no way. It's an impossible problem. This is extremely interesting. Okay, so cultures all over the world are very different. The world is a huge place, okay? So I won't go through all this, but I'll tell you what all this is. So depending on your culture, there's things like saving face. In other words, what white lie can I tell so that I don't look like a fool? People get into all these negotiation patterns, okay? See, for example, in UK, the British are always, like very people, don't rock the boat. Don't rock the boat. So then that is their, philosophy of basically dealing with deadlocks, okay? And then some other country, Germany, all right, we can all get through this, just follow the rules. We'll get there. France, right? Oh, come on, philosophy. Let's talk philosophy. We can all solve this, right? We're all human beings. And then Italians, we see clarity. It might even be like fist fights somewhere, right? Like, just duke it out. Sweden, just beat around the bush. Don't even talk about the problem. Avoid. So it's so fascinating how these diagrams are formed. But they're based on real world, analysis of how people behave. Look at Hungary. So look, cooperation, but still be critical. Watch the other guy. Poland is so interesting. Like, whoa, zigzag. Okay, so then these all happen because, there are deadlocks in negotiation. You literally go to a so-called negotiating table, and both sides are trying to get massive amount of things from the other side. The other side's goal is to not give those things away because they want maximum stuff from you. Deadlock. Okay. So then, many ways of saying this. There's only 4 slides and I'm trying to time it. But we can easily talk to this. All these notations, don't worry about them. They're pretty simple. T1, and here it says T3, 2 transactions. And then here it says, RI, W. Is it 1 or I? Can you even tell? 1. R is basically read, W is write. So this means it is trying to read X and probably take the value in X and trying to maybe like write to Y, maybe double it or multiply them or something, right? So read followed by write. But the point is that X and Y are involved. You have X and then you want Y. Meanwhile, this other one has Y followed by X. So Y and X, same deadlock. Just read this. C, by the way, means commit, okay? So these notations we use just to say, if this all didn't happen, then I can read, I can write, I'm done. Likewise, if T1 didn't come and screw me up, then T3 can say, I can write again. So it doesn't matter, some reads and writes. By the way, if all of them are reads, then there's no problem, okay? So somewhere when there's a write involved is when deadlocks happen, obviously. Okay, so think about it. Therefore, one in just a 2 cell situation, both can be writes, or at least one of them has to be right. Right. That's what all this is in too many words. Brown used to tell me, you talk too much, too many words. Okay, so this one is here. You can read like a Microsoft article about all this. Carefully explained. Cool. There's a whole book, by the way, you can go look for it. But chapter 3 is extremely well written. And I just, stole the picture from there. It's a lot about schedulers. People used to worry about all this way too much, like maybe 2 decades ago, when it was not very clear about the best way of doing things. But now we have best practices. So if you log on to Amazon Cloud or even live in SQL or Oracle, for some reason you have shared tables. None of this is like a problem. There are ways to robustly solve it. So it's just a matter of knowing the terminology, understanding a little bit, okay. Okay, so then I'm not obviously going through this because it's really unnecessary or more useful things to talk about, but there's deadlocking. Okay, so I've obviously skipped like incredible amounts of things, okay. FYI. Okay, so what else do we have? Yeah, timestamping. All right, so timestamp is practically how cycles can be detected and also dealt with, because every transaction, meaning every read, every write, has a unique timestamp, which can be just a simple, like a incremental number, like a monotonically increasing number. Every transaction gets an ID, 1, 2, 3, 4, 5, up to billion. You can do it stuff like that. Or there's a global clock for the entire world, a globally unique ID, a globally unique identifier, GUID. So what is this? Somebody should tell me, okay? CPP.sh is an online ID that you can run quick C++. If not, I'll just ask you, just like a simple call, like a C++ call, but then tell me what the call is about before I run it. Okay. Ooh, that's not good. Okay, I'll ask you. I'll just try it one more time. So what is a way to use like a system clock, a Unix system clock, to get unique ID, and why is it unique?
I'm going to speak because it's faster than type. The Unix system clock is basically the number of milliseconds passed after like exactly 12 a.m. of January the 1st, 1970. It's unique because basically it's very hard for you to get like 2 requests at the same millisecond. That's my understanding.
Extremely smart. Perfect answer. So the time command, right? The standard C++ time command will tell you when you run it, how many seconds have elapsed since January 1st, midnight, 1970. You're right. If I do it every second, like playing a video game, 97, 98, this is cool, right? Every second I'm compiling and running. Hey, cool, I lost 2 seconds. Powerful. A life flashing by in front of our eyes. We're all getting old. Oh my God, look at that. No, stop it. See that? Yeah. every second, just time going by monotonically. So that can be used by some system locally, okay, as some kind of a timestamp ID. But that's pretty cool though. Just simply time now. Cool. What a thunk. Okay, now you know. Time command. And then, I started to show you, right? It's got some nice history. Okay, so I'll just say January 1st, 1970. Almost nothing comes up. Or I'll just say epoch or something. Okay. 1970. Because the time is also called epoch. The next. Yeah, in many ways too. And then you'll get the Wikipedia article. So like here, right? Exactly, midnight UTC, unique epoch. And afterwards, then you get the Unix time. Narrative.io. Instead of reading, I thought I'd just show it to you like that. That's what we're in. Okay. All right. So that's a form of getting a transaction ID. That's all. You just have to be monotonic, in your system. It should be consistent, meaning somebody that comes after you would have like a younger number, so to speak. Younger could be a bigger number, even smaller number, possibly. Probably bigger number. You can just do a plus plus. Okay, then how do we practically use it? We do this using timestamping. It means every transaction has a timestamp, and we would use that timestamp. So why does it say 2 additional timestamp fields? Okay, so some things that I say I won't explain, but you can think about it. But I'll just simplify it for you. You don't need the 2 timestamp fields. Conceptually, it's only 1 timestamp. It just means when the transaction was initially started, before all the locks were acquired, what was the ID? Literally at the start of the transaction. Okay, so just go with 1 ID for now. All right, so when you have the 1 ID, these things are no big deal, okay? Memory needs processing. You have more RAM than you would ever need. It's no big deal. Our CPU is like multi-core. So just ignore all this, okay? Okay, because, it's so useful. And I will definitely magnify this because I want to show it to you. So what happens is this. These are called deadlock prevention. Once again, you detect cycles and you break it. But then there are 4 different ways in which you can do it, okay? So I'll read this and come back to our 4 rows. There's one called wound weight. See, this one here is literally called the wound weight scheme. You can Google it, the wound weight scheme. And the other one is called the weight die scheme. But there are 4 words. There's a weight word, die, wound, weight. They're applied for 4 different parts of this little table, meaning weight goes here, die goes to the bottom, wound goes to the top, weight goes to the bottom. So even though you call it weight die, there are 2 different schemes actually. Even though you call wound weight, there are also 2 different schemes. So there are 4 different schemes in which we can use to kill a transaction so that the other transaction can succeed. This is still all about 2 transactions, okay? They're both in a deadlock. So then assuming a deadlock has happened, what are we supposed to do? You can do one of 4 different things. I'll just show it to you here. It's pretty simple. Okay, so in the top row, the older transaction, meaning a transaction that already has been happening, some locks have been already given to it because it started before this transaction. It's the one that wants a brand new lock. Okay, that's for the top row. Meaning I'm already given some locks and I want 1 more lock. In the meanwhile, you came along after me and you're given some locks. But the locks that you were given, I want. So the older one wants the transaction. In the bottom row, it's the opposite. In the bottom row, the older one already had some transaction, but the younger one wants what the older one wants. So the younger one is the one requesting. It says, give me your lock. So what should we do? Okay, let's do the top row first. The older one requests a lock. So in the wait scheme, the older one is simply going to wait. So if I'm older, I want your lock, then I'll not do anything. I'll just wait, really. Just hang until the younger one gets the lock so that there's no deadlock. And then after you finish, I'll get your lock. That is called the wait scheme. So then I should not do die, I should do wound, because let's do the top row. So wound means the older one will literally say, I'm older, so the younger one should roll back. So take the younger's lock and the older one gets it, then the older one will finish, and afterwards the younger one will get it. So in this cell, the older one simply waits. In this cell, the older one gets impatient and says, mine, I'm older, respect. Just grabs it from, it's called preempt. Preempt means just take it. Okay, so wounds it, okay? So the older one will wound the younger one, kill it. Then the younger one just goes back. All right, so here the younger one finishes. Here, the bottom row, it's the opposite. The younger one is the one that says, can I have your transaction, please, you're older. The die scheme, the younger one says, oops, sorry, I wanted it. I'll go back and come back some other time. Good luck finishing your transaction. So T1 will then finish. T2 just literally goes back, even though it wanted the lock, where it's willing to kill itself. That is called the die scheme. And then here, the younger one, again, says, I'll wait for the older one, respect. You go first. T1 finishes, T2 gets it. They're almost like diametrically opposite, right? It's very interesting. Okay, so just think about these 4 schemes. That's all it is. There's a lot packed in here, but it all makes sense. And it's all for one purpose, which is there are two different transactions. They have timestamps, and then they both want the same thing. And so then who will you give it to? That's really all. Too much fun with timestamps. So that is this idea. In other words, you can pick any one of the four schemes. They all work, okay? What is the difference between waiting and dying? So dying that's a good question. So waiting means you hold on to the locks that you already have until you get the rest. Dying means you completely give up all your locks and you go back to the back of the line. Very good question. So wait means you don't have to get all the locks over again. Say you want 20 locks. You already have 18 locks. Wait means you just wait for the other two. Dying means you throw away the 18 and you go back and get all 20 again. Needless to say, waiting is better than dying. Could the die scheme cause problems when T2 dies and goes back? Yeah, sure, absolutely. Yeah, so if T2 is completely out of luck, right? Every time it comes back to, wanting more, it's caught in more and more deadlocks. Totally possible. Yeah. They're highly unlikely, but definitely possible. Yeah. No such thing as bad luck in transactions, right? But say there was, then there's one transaction of the millions would just never get all the locks at once. Okay. But statistics probably says it not happen. Okay. So then that's all it was. You simply find out, like using a cycle detection, that T1 and T2 are involved, and use timestamp to deal with them. This last one, it's a fun way to end this, is so you don't do any of what I told you. Just let things happen. Meaning, say transactions literally override each other. Thankfully, we have the log. Yeah, exactly. It's like starvation. Are you talking about is deep answering Hamza? Yeah, exactly. Starvation can happen over and over again. Potentially unlikely, but can happen. All right, so in the optimistic approach, reading is simple, right? Just simply a transaction reads, executes. You know what this update a private copy. You always update private copies. But the thing is this though, well, I guess what they're saying is before you commit anything permanently, okay? So in this scheme, in a deadlock indifference scheme, everybody's running local copies. You can always go in the log and analyze the log to see if there's any overriding that happened. And then you can undo potentially, transactions that damaged each other's work, and then only commit the changes, that are not inconsistent. In other words, the indifference basically says, I'll be optimistic, I'll let, potential overrides happen. Suppose you have an archaeology database, okay? Suppose you're, a historian, you're running an archaeology database at UCLA or something. And then they have thousands of artifacts, like the Hammer Museum that they have. That catalog, the museum catalog, is hardly updated every day. They'll be lucky if they update it every decade. You don't get archaeological, digs every single day from Egypt, right, or something. So in that sense, that database scheme would not have any kind of log management at all. It basically says anytime any transaction wants to update any cell, just go ahead. And then you can always look at the logs before you permanently commit. And if the logs had one transaction writing a cell and then a different transaction overriding it, then at that point you can decide which one to keep. That's really all it is. Okay. That's the validation that I'm talking about. Okay. 6:26. This is perfect. I'm about 10 minutes late, but it's okay. We'll only talk till about 7:30, okay, and have some nice discussion questions to ask you. So in the end, transaction management came down to this notion of deadlock cycle detection at the lock acquisition stage. Okay, in this scheme that we talked about called the strict two-phase locking, because there are other schemes that I didn't bring up yet. And in our scheme, just to remind you, the graph looked like a Mayan pyramid. There was a growth stage, and then there was an execution stage, and then there was over time release stage. Locks obviously take time to acquire. Magically you cannot get all locks at the same time, but unlocking is a different beast. So you can start to think about what I might ask you, but for now we'll just say it does seem like locking definitely at least must happen over time. You cannot get all the locks that you want all at the same time like this, like that. And then likewise, this we just draw a flat line because nothing is going up. The number of locks is constant. But what about here? Okay, there's different things you can do. Okay, two other things you can do actually compared to what we did. That's only one of the three things that are possible. Wow, what else can you do? Okay, so then that's all coming up in the discussion. How do you implement a transaction scheme on a database? I mean, there are processes there's a lock manager process, okay? Okay, so I'll answer you probably in the very best way possible, Molly. There is a database called KubeRead. That one. KubeRead happens to be like a nice open source database. It means you can download the code for KubeRead. If you go look around, in that code, you will actually see a C program that uses good old pointers to keep track of all the locks that implements 2PL. So you can actually see the 2PL algorithm implemented in KubeRead. In other words, they're just processes. Once the database DBMS process all start up, it's a bunch of processes. There's transaction manager, lock manager, there's admin authentication manager, and then SQL engine. They all start simultaneously. Then when users start to log in and start doing the transactions, then the lock manager, one very specific process, will actually do this lock thing that I just now talked about. Anytime transactions wants, reads and writes, then it's lock manager's job to actually assign those locks, and when the locks are released, to put it back in the pool to allocate it to somebody else. So it is done with basically processes like Unix process. Okay, so KubeRead is actually very cool for many reasons. Okay, one of them is you can read the source file. Next, you can also read the blog. So hopefully they have a blog somewhere, or you can Google it. That blog has amazing articles about all of these. Yeah. So go to downloads and get the download. They have some pretty, like I said, illuminating articles about everything actually, read it, okay? So in this like Node.js, I think they've got some more modern things. If you Google, go back to some of the older things, they'll actually talk about database issues such as transaction management. Highly useful. I mean, these are cool, but they're too low level. I mean, even these are useful actually, so you talk to JDBC. I might find maybe more like targeted articles that I would like you to read. I'll put it up in extras, by the way. But then for now, you just know that if you go there, you're able to, get to the blog. But even better, you can also get the source. Source need, right? Right here, downloads. Okay, so that's very cool. You can actually get KubeRead. Wow, or get the source. Older versions, tools. Okay. Wow, it's a lot, right? Drivers. Ooh. Okay. The next what I'm going to do is, without missing a beat, exactly 6:30. Distributed DBs. Hey, what just happened was without the CSS. Without CSS making all this look pretty, things look ugly. No, now the CSS is cached. Okay. For a brief while, good old times Roman flashed by. The world looks so horrible. Okay, so what is distributed? Two answers, meaning two things are distributed. By distribution, I mean your transaction will now run, or data is stored, on more than one machine physically separate from each other. And your transaction must run on all of them. Then it's a distributed transaction. So what is distributed are two things. Data. The tables themselves can live in many different servers. Amazon does not have the entire business at Amazon.com at all. Okay? Probably have thousands of servers. But to you, it all looks like one unified little picture. So your data can be kept in many different places. And or the computation, which is the transaction calculation itself, can also happen in multiple places. And these are two different things, right? Data and computing. So memory and like storage and computing. They both can be distributed. Either can be distributed. Or neither one can be distributed. They're all like local, but that's a world we don't have anymore. So I'm going to walk you through all of that, okay? And then the same question we asked about how do you do like locks. Now you do what's called distributed locking, where all the individual machines on which your transaction is running, they should all have the same lock manager running, meaning they're all like different copies. And then every one of those individual transactions, the pieces of your overall transaction, 5 pieces here, 5 pieces, what, they all have to get locks. They all have to get locks, and they'll all be done. But there can be problems when there's some miscommunication, meaning one of the nodes, one of the machines is down. And so then out of the 20 pieces of your transaction, 15 can succeed, but those other 5 on that machine, they're not able to succeed. So how will you unroll all of them? Okay, it's a very cool architecture. You might know this, okay, if you took a database class, it is simply called two-phase commit. Two-phase, this part two-phase is the same acronym as before, two-phase locking, two-phase commit. But now we call it two-phase commit. And it's a very different algorithm. It's almost nothing to do with locking at all. So just that letter is different, but a very different idea. It's a radically different idea and a cool idea again. So what does it all look like? It looks like this, chapter 12. Okay, so I told you everything happening in one place. By everything, I mean data storage and also computation happening just on one computer in the entire world was from the 1960s and 70s and part of the 80s. it's not true at all anymore. Those are called centralized databases. So the IBM mainframe days are exactly that. So the IBM mainframe was ultimately a machine that took up almost an entire building. And then it's called the computing center, right? A whole building. So people are on different parts of the building or maybe different parts of the city, but they have a wire that literally just goes and straight logs on to that machine right there. And then your data is stored in all these, tape drives and stuff like that, right? In other words, everything's, so that tape drive right there, all the whole company's data is all stored like right there. So that is how it doesn't matter where people are. They have dumb terminals. They just simply log on. But then all the computation and all the storage happens in one place. That is called a centralized system, as opposed to a distributed database. It's the exact opposite of a distributed database. But this is how things started. And then we realized how bad and how dangerous this is to put all your eggs in one basket. And now the world is so huge, you don't want the entire world to go to an Amazon basement and run 100 million transactions, on the computer in the basement. So there are any number of reasons why this is a really, really bad idea. If some terrorist, blows it up, and the whole thing is gone, right? So you need, for too many reasons, just never do this. But this is how it started. You had to start somewhere. All right, so that was the notion of a centralized database. A centralized is exactly opposite of distributed. So I'll walk you through some of these scenarios, okay? All right, so in a centralized database, there's exactly one thing, okay? It's the DBMS right there, local database, so data is here, and everybody logs on through the DBMS engine. This is the one that authenticates people, serves data ultimately. So then if you are somewhere, you're a dumb terminal, meaning there's absolutely no computation, and you want somebody's payroll, you want to give somebody a salary, raise, then the salary raise request, like override somebody's cell by 10% more value, comes from here. Then the database carries out the operation and then sends a response back that it's okay, done. Everyone has to go to one place. And then that's single point failure problems. So the factors are globalization. Again, the internet came and said, this won't work anymore because people are in different time zones and they're using your server 24/7, your machine's going to crash. So don't do it. Likewise, web services are the exact opposite of this. You don't run everything in one place at all. This one will make calls to so many other machines. They'll make calls to so many other machines. It is an entirely distributed way of doing things. It's too dangerous to do it all in one place. So that's another reason. And then social network. I mean, these are all the same. You have now worldwide users, right? So they cannot come to one server. And then you have also many types of data. There's tweets, videos, it's too many. It's all too much for one machine to handle. Your Unix address space is not even enough to actually store all the data. You cannot even do the computation. So you need different machines with their own address space. Okay. And then I don't even know what this means, I guess if you have data warehouses, data warehouses by definition have a massive amount of data. They can't all run on one machine. So there's many reasons to never centralize. That's the thing in the past. But if you boil all this down to just two reasons, so it sounds the same. It's really these two. On the one hand, you need data super fast. So again, if nothing else, if the whole world went to just one catalog, somewhere in the world, everybody would be slowed down. But you want massive speed. You want things at the blink of an eye, right? So that is one reason to not keep it all centralized. And then the other one is, again, your whole business, your users are all distributed. So you want to serve people where they are and have local updates and so forth. So we have a new D in front of the DBMS. We call it a distributed DBMS. It's distributed because physically, many servers, you can loosely call them servers, they're all database engines. They're all connected one way or the other. You can reach from everyone to everyone else. So your transaction, you're buying something, will then potentially touch many of those nodes. So I'll use words like node, cluster, okay, they all mean the same thing. So a cluster is just a series of machines that carry that are connected. You can call this like a node cluster. So come up. That. Okay, so that should be enough to get everybody. So then maybe my transaction would have to occur here, here, and here. Maybe your transaction has to run here and here. Somebody else's transaction has to run here, here, whatever. So that is really what the notion of distribution. But rather than 5, imagine 50,000 or even more than that, 500,000. So Google has easily 100,000 machines all over the world for their search. These are like unimaginable numbers. Okay, they won't even tell you what the real number is. But that is the kind of order that we're talking about. So this is not trivial at all. Then how can you guarantee? It doesn't mean my transaction uses 500,000 machines. Okay, even if I use 10 machines, how can I guarantee that they all work? That is the point of the whole lecture. So you will not centralize it for sure. All right. So again, why do you not want to centralize? Because performance goes down and then the maintenance costs for the one machine goes up. This is the biggest of all. The disk is constantly just spinning, right? Yeah, absolutely. Yeah, the transaction by itself, right? Well, like what you call a transaction is simply a series of reads and writes that involve many tables. So even by definition, I would say this has always been true. But now what is additionally true is those parts that we're talking about are not just on one machine. Like in other words, say there was a table here, table, right? This is still true that my transaction has to run on all the tables. But now additionally, the problem is it has to run on this table, that table, and this table. Japan, UK, California. So then how can I still succeed? Makes sense, right? Okay. Moving on. Yeah, so then what happens when things are distributed? Okay, so I won't read them, they all mean the same thing, okay? No address space, no disk space. You physically run out, you're on building space probably. And then this means your design is centralized by whoever the heck is running that building. So the whole world is basically held hostage by your bad design. That may be another reason. All eggs in one basket, not done. So the entire opposite of that is distributed. So you want to distribute it all. And the biggest reason for that is the web. So every person that has a phone is a database user. That if nothing else, browsing things all the time, an eBay auction they like. And then all of a sudden the auction goes to a price that they can afford. Wow, I'll click on it, I'll bid right now. At that point, they're writing data. So every one of us, the billions of people in the world can write data somewhere. And so then things had to evolve. And then interconnected systems, data. And again, it's all over and over about data on computing, okay? So they can be distributed and then centralized. Just forget all this, okay? This is what I showed you, IBM. Okay, all this. Yeah, this says where did DBMS come from? They came because of the internet and then smartphones. And then, yeah, this is application as a service. Again, any machine now can collect data from anywhere else. So if you want the weather data, weather.com, then question mark, zip code equal to 91214, then who knows where the machine, the weather.com sent my request to. Maybe some other, weather service actually holds all the temperatures. Maybe somebody else holds all the humidity. And they have to query all the services, put like a nice weather report together and send it back to me. So that is by nature a distributed transaction right there. And then I don't even know what this is, mobile. This might mean that these days, streaming intelligence, meaning, the CEO can hold up a smartphone and in a small little screen, they hope to see a real-time update of their business from all over the world. Anybody that buys anything, a small little blip goes up on their phone. It's stuff like that. So then that is also highly distributed. It means your transaction cannot all be in one machine. They need to be fast enough for your little mobile thing to update. That's what I would say. Okay, so advantages and drawbacks. So what is the possible drawback of distributing? Oh, come on. I would just cross this out and say these are all like fake news. So nobody cares about all this, okay? We have no better choice. There's no better architecture. If you think you have a better idea, tell me, okay? We're not going back to centralized mainframes anymore, okay? So this is all just simply to balance out those bullet points. I would remove all this. On the other hand, what are the advantages? These are all true. You have things called content delivery networks, CDNs. So CDNs will make a copy of a database and keep it somewhere else, make multiple copies, so that anybody in Japan can then log on to amazon.co.jp. If somebody's in Canada, amazon.ca and so on, or amazon.co.uk. You keep data close to where people are. That way it's served fast. Again, these are related, okay? So fast data access processing, and then the sites can independently grow, by the way. So when all is in one, like I said, one Unix address space and one disk space, the machine can only grow so much. That's called vertical growth, by the way. So there's horizontal growth and vertical growth. So scale up and scale out is what the big data people call it. Scale up is vertical growth. Only one machine, meaning only one set of disks, only one CPU, holder, and then only one set of memory banks. Your RAM can max out after maybe 128 gig, right? We already have your 16 core right there. We already have your 2 terabytes of address space. There's literally, you cannot build anymore. This machine is completely maxed out, okay? So that is one way to look at it. That is called vertical. It's called scaling up, like vertical build out. So it's not the way to grow databases at all. Like say Facebook buys like one other big business, right? They buy something else. Say they buy Telegram or something. Then they get all of the users. So this is not the way to add more users. Instead, we prefer this approach. It's called horizontal scale up, or it's called scaling out. You build more and more machines on your network and you hook them up. Say the machines were already hooked up like this, okay? So it was hooked up like that. But now, if more users come into your business, I'll add one more machine, one more node to my cluster, then put all the new people here. When that fills up, I'll add one more node, and then I'll connect it over here. These, by the way, Fry's is closing. Fry's Electronics closed as of last night. It is so damn sad. What the hell? It's so unfair. Come on. I don't know if you know, but Fry's Electronics is actually closing. Why would I bring it up? Yeah, exactly. I couldn't believe it. Oh man, I know the layout of the Burbank Fry's inside out. It's in my head. I just wander through every single eye, look at every single thing that they ever have. It's crazy. Possibly. But that look, they never cared about the users, by the way. You go into Fry's and there's nobody to help you on your own. But the difference is this though, between Micro Center, Best Buy, all of those. In Fry's, you have no idea what you're going to find, okay? Some crazy thing, made in China 10 years ago, some cool Linux, MP4 player, $5. Oh, I'll just take it, just open it up. I'll take the screen and reuse it. So I used to go there for parts all the time, spend thousands of dollars. So why did I bring it up? Because in scale out, you can walk into Fry's, buy like a 4 terabyte Buffalo drive or something, a Western Digital drive, and then come to your business and plug it in, and then start migrating users. Just simply, hot plug in, meaning I don't have to bring the thing down at all. It is that easy to scale out, okay? So I just add more and more nodes to my cluster, just by commodity hardware. CouchDB, in Couch, that's called commodity. That means I go to Fry's and I spend $100 and I'm growing my database. So growing your database is very easy if you do it by scale out, okay? Horizontal scale out, not vertical scale out, which means it must be distributed. That's all this says. So that growth facilitation is what that is. I don't know what improved communications is. Reduced operating costs. Well, per center, meaning if they're all distributed sites, then no sites cost eventually just goes up. It's weird. This is very true. Less danger of a single point failure. Yeah, the whole internet was designed exactly, for that reason. The Soviets could not just blow up like one half of the country. It will still keep working. So likewise, there's no single point failure. These machines are even backed up. Like any data here, this is multiple backups, multiple copies exist all over the place, all hooked up. So almost anything is, not going to fully destroy it unless you bring the whole thing down, okay? So it is highly robust as opposed to all in one place. Oh my God. Imagine this in a basement. The basement floods over the weekend, right? Holy crap. Everything is gone, including your backup that you had up there. So that is clearly not the world you want. And then this is also true because when you distribute things, say these are web services, right? You have no idea what machine that even is. Is it an IIS Microsoft server? Is it Ubuntu? Is it Nginx? Is it God knows what, right? Is it Oracle? Is it NoSQL database? We don't even care. It all just somehow works. So that is the notion of independence. It's more than processor independence. It's also operating system independence, it's vendor independence, programming language independence. There's all kinds of independences that you will actually get. So that is why none of this matters, okay? Just ignore it. It's pure advantage only. Like I said, we have no better way to do it. Okay, I'm going to go through the slides now. You can distribute either the calculation or you can distribute the data, okay? Or you can distribute both, actually. When we say database, we just mean data. So processing is literally, you have some data, maybe part of it is sent here, part of it is sent here. They're both working on it, okay? So then that's distributed processing. This means your tables are stored. Say you have 10 tables in your homework. 5 tables are stored in one machine, and then 3 tables, 2 other tables. 3 different machines are involved. So do we store? Absolutely. Oh, this is a good question. You can keep it near so that if one of them fails, you can very easily get to it. But you can also do exactly the opposite. If you're paranoid and you think that the whole Pacific Northwest is going to be rocked by a huge earthquake, then Amazon says, put up our copies near Australia, as far away, from here as possible. So both. But in general, it's actually near, I agree with you. Because that way, the rerouting that can happen, it's almost like not noticeable. Yeah. There's even some algorithms for actually that. All right, so a fragment is a very cool idea. So I want to tell you about fragments. You don't have to do the whole distribution of the entire table, okay? You can even break up a part of a table. So that starts by saying, what do you mean by distribution? So a distributed database that is made up of tables, say there are only 3 machines. Say there are only 4 tables, okay? So I can have table 1, table 2, table 3, table 4. And together, all of them contain your business. It's like one distributed deal. So a transaction has to possibly touch like more than one table. But now you can go to a table and even break it down into small chunks. They're called fragments, okay? So this all, again, goes with NoSQL as well. So things that I tell you will not repeat too much in NoSQL. When you take one little table, you break it up into, in this case, 4 chunks, Each chunk is pretty much a fragment. Fragment means a piece. Fragment. Or have a part or something, right? The part breaks, then those are all fragments. That's where the word fragment comes from. It's fragments, okay? All right, so then every little piece together, they form the whole table. Those fragments can also be distributed. It means in this table, I can keep only these two fragments here. These other two fragments can actually go over here. And fragments can also be duplicated, by the way. So these two fragments, I can make a copy and put it on this node over here. And these two fragments, I can copy and make the copies be here. So fragments are smaller than tables, almost like a page, but a different idea, bigger than pages, okay? So fragments are what we distribute. I might as well tell you, there's also a different way to fragment. Again, these are rows. Just if I don't tell you, these are rows, like one student, okay? And these are all students' columns, major and GPA. So the most common way to fragment is what's called a horizontal fragmentation, which is I take a bunch of students, like 1,000 students at a time. USC has 40,000 students. I make 40 fragments and put them in 40 different places. You horizontally break them up, horizontal fragment, all the rows, but only for a select number of students. It'll be all the, A to H, H to M, what. That's one way. The other way is what is called vertical fragmentation, where you take the same rows and columns, but now you break it up based on columns. You say, I'll store the first name, last name, and GPA somewhere else. I'll still store the student ID, definitely. And then I'll store student ID followed by major graduation date advisor somewhere else. You need the student ID to be common, right? But you break them this way. Then it's called column fragmentation. You can even mix them, by the way. You can do a column, and within this column, you can do fragments, horizontal fragments. Okay, so there's a lot there. In general, we call all of them fragments, and fragments can be distributed. For now, that's all. All right, so then just a bunch of slides, they go fast, they're pretty simple. What does all this mean? What does distributed processing mean? It means the calculations are done in more than one machine, that's all it is, okay? So imagine there are two people, right? And there's one database. And so then the idea would be that a part of the database is being updated, like over here, payroll data, maybe the salary changed. And then this machine then has to receive that and generate some kind of report over it. So the report calculation is going here, just like you're doing for your homework. And then the actual salary increase, is being done here. And they both obviously go back ultimately here. So only one copy of data. Sharding is the same as fragmentation, 100% the same. Shards are fragments. These are called pottery shards. Okay, yeah. Shard is a fragment. Okay, pottery shard. By the way, you can use machine learning to put them back together. But that's a topic for another time. The exact same thing. Practically get the same thing, right? So sharding and fragments, they're the same. Okay, sharding can be called a verb. You don't say fragmenting, although you could say that. The results are fragments. So you shard a table to get fragments, but they are the same. All right, this was too simple, okay? It just means, the calculation happens on more than one machine. That's distributed processing. On the other hand, you can also, maybe all calculations happen on one machine, but table A, table B can be in two different places, okay? And then a transaction has to get data from both of them. Then you call it distributed databases. I've said this before, so there's nothing more to say. And then you can do both. Then you call it fully distributed. In general, that's actually what happens, meaning that your transaction runs on many machines, also contains data on many machines. It's this modern world. So distributed processing and storage then we call it fully distributed. Okay, so then what happens in the fully distributed database? You pick up your Amazon app and you start ordering. So then the Amazon.com receiver, the proxy, gets a request. That's where the thing starts. And then it analyzes your request, meaning it knows what you're trying to do. So what transactions are involved, and therefore where your request has to go. So all the distribution happens here. Then your request goes to multiple different machines where they can serve you. Say you buy electronics, it'll probably go to an electronic server. Say you buy clothing, probably go to a different server. Say you're trying to book something else, a vacation or something, right? Then probably, or Amazon Prime, I don't know. They can all go to different places. And then in the end, the request is just simply transactions, the read-write operations, and then that happens. And then at the machine, meaning each DBMS that receives like all these requests are then doing like all of these locally, okay? So locally, they must ensure consistency, meaning transaction processing, the whole log management, all that is happening on every individual machine. And then, they all do their thing, meaning every machine computes a part of it. And then they can all send the request back to the main proxy, and the proxy will send you a response back to you. So nothing. You're just sitting on your couch and ordering things. But then many machines went to work. They all provided data. They all provided computation. and then it all came back for you. It's called distributed processing. Again, two computers, meaning two different processes can be running, and also two different fragments, okay? So this is fully distributed. It's easy to just think about them, okay? So don't get caught up in all these words, but that's all it is. This is the real world, so eBay, LinkedIn, they all work this way. But the user has no idea about any distribution. They have no idea data is distributed. Most people think that, when you go to Amazon.com, you're buying something from Seattle. It's probably not true at all. Okay, but that's what people think. Or you think you have the whole catalog to yourself on your little phone. That's not true either. But it's good for people to think that. So they have their own local version. It's not true. All right, so then to serve transactions, meaning to handle transactions, I should say, and map transactions to individual tables, the process that does it is called a transaction processor. It knows when a SQL command comes in, basically, what tables are involved. Okay, and then it can arrange for the calculation to happen. So ultimately, it's responsible for all the calculations. But in the meanwhile, tables are involved. So then the table requests are sent to this processor called a data processor or data manager. Transaction processor, transaction manager, same thing. Data processor, data manager. There's a clear line of separation between them because the data processor has no idea what the transactions are. It doesn't know that somebody's being given a salary in a raise, right? It just says, access me the salary, column for city. That's all it is. So the purpose of this is simply to serve data. And this one, on the other hand, does the more complex coordination between all this data, and then it does the calculation. It's just an arbitrary separation, meaning some machines on your network can function as transaction processors. Some other machines can function as data processors. They can send distributed data requests. In general, some machine can actually function as both of them. They're two different processes, that's all. So a machine can be both transaction processor and a data processor. These are just conceptual, so we don't even worry about too much about them. And they can also have data and they can do computing as well. They're not just purely a supervisor. One of them just takes on like a supervisory role, meaning that the overall request comes there and they forward, okay? But they also do some work. Okay, otherwise you cannot afford to waste processing and just sitting there and getting requests. So they have to do some other work as well. This all makes logical sense, right? It's all common sense. Okay, so therefore, what I told you, transaction processor just is the one that is receiving the transaction, and then it'll then send the data requests to a data processor. It's also called TM, and then data processor, aka DM, serves data. Pretty simple. And it looks like this. Some are pure TPs, some are pure DPs, some are both of them. Okay, no big deal. Ultimately, they're connected. That's what matters. And this is not even the internet, okay? So even like a local area distribution, like a local area network, all you need is something called a protocol. Even the software application, the database itself can provide some protocol, so the machines can all exchange all this data. Like, what does it mean for a transaction to talk to a data processor? How can it send a table request? What does that mean? There are very specific ways in which you request and you return responses. This is called protocols. But in the abstract, you're just saying, I'm asking some other machine for a table or a part of a table, really. Okay, so then I'm not going to read all this. It just says the data. Yeah, so in a way, the transaction processor is in between the user and then the data processor, right? That's all it is. So that the user is sitting here, and then they make a request. They want to buy something. The transaction processor gets the request and says, "Wow, the data that I want should run here, and that's also available here. Then maybe they should send data over here, and then this can do all the calculations, send the result back to me. I'll put it back." So it sits in between the data and the calculation event and the user. So the user, then you have the transaction manager, and then the rest of the backend data and calculation. So in that sense, it's like the middle person. Okay, so then therefore the TP is ultimately responsible for the whole transaction because it is the one that receives the transaction. DP doesn't know about any transaction. All it gets is data requests, okay? And then it can service that. This is nice because it can focus on data. Okay, otherwise nothing more to say. So then, yeah, this is actually interesting, right? Look at this. That you can draw a simple table and say when you have single versus multiple, data versus computing, how many possibilities are there? Obviously 4, right? Okay, so single process, multiple process, single data, multiple data. Where's that? Yeah, like over here. So these are the 4. When you have single process and single data, that's basically the mainframe, okay? So everything running in one place. Or when you have multiple processes, but all the data is in one place. That's classically a file server, like a LAN file server. The data is all sitting in one place, maybe a whole bunch of Excel spreadsheets. And then many different people want different parts of the spreadsheet. Like I want the salary spreadsheet, you want the R&D spreadsheet, and so on. So then the file server just serves, and then they can all do the independent processing. This is a classic LAN architecture, okay, from the 1980s, where you have all the data in one place, single site data, but multiple site processing. Even PCs, just local PC applications can get stuff from a file server. So that is possible. And this is fully distributed. You have multiple sites, all the clusters, they're all holding some data, and also they're all doing processing. So that's a fully distributed DDBMS. And then there's this fourth part, where conceptually you can imagine that there's data in many locations, but they all send all of the data down to just one process, okay? That is possible. But in the real world, that doesn't happen. So of the four theoretical possibilities, only this are practical. It's not very practical. There's basically no use to hold the data in so many places. And rather than compute it yourself, no need to send it to one place. So the fourth thing is X'd out, okay? There's no such thing. Okay. So it's too easy. That's why there's 3 and not 4. Okay, some more slides to say the same thing. I'm gonna go a little faster. This is simply mainframe. Single site, single data, processing data, all of it. One host computer and everything's local, and then nobody else has any power. They're just logging in with dumb terminals. So in the IBM mainframe days, that's what happened. We call them dumb terminals. They just give you like a username and password and very clacky keys. Tap, 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 tap. And you start to see data. But then the machine is not doing anything, it's receiving data. So then it might look like this. No matter how many machines there are, they're all ultimately coming to just go to one place, okay? That's where the calculation, everything happens. The results go back. Mainframe, just simply in one word, mainframe. Multiple processes, single data. So the single data is served by a file server, and then multiple processes can process it. That's what this is. So file server is network file server. Client server architecture. Because the server would be the file server, the clients would be all the multiple processes. They're all getting data, but doing their own processing. And why do it like this? Because then you can all just talk to one of them. Then they're all these processes are not talking to each other. They're all like going through like one node. And sometimes, that is useful, like hub and spoke architecture, right? Like this. So then you have this one machine, the file server, and everybody else connects to it. It's kind of topology. And so then maybe you can keep all the individual traffics minimized, like they all don't do cross traffic, okay? A different architecture. So that's the architecture for like a LAN. You can even just Google all this to find better diagrams. Just say file server, okay, and just say LAN. You'll actually see things like what I'm drawing. Because all the client PCs need to connect to Ethernet usually. And then that's what the machine physically looks like. Then you'll see these diagrams like that, file server. But then this is just 3, but you can imagine like a whole bunch of them all around, more like that. Okay. So then the network is what connects all of them, okay? Again, there's the file server. You can even have little clusters within clusters, like work groups and so on. But in the abstract, they're all ultimately coming to the file server. Because that is the one truth, that's where everything is. All right. Storage area network. So the same idea can also be done for, like a local cluster of distributed storage as well. Sense. Storage area. And then, but if this happens, right, there's only one. So the file server idea, only when you say MPMD, you call it full distribution. When you say MPSD, that S single data is not fully distributed, because data is not distributed. That's what this says. Okay, because, data is all in one place. This is now fully distributed. This the whole point of all this is the whole world today. MPMD, you have multiple processors, multiple sites, everything is multiple. And then how do you classify them? This is actually very fascinating. When you have a fully distributed network, say Amazon, Yahoo, eBay, how do you classify them? On the one hand, you can call it a homogeneous DDBMS. So then homogeneous DDBMS means all of the sites are running pretty much the exact same, even software, like they're all running Oracle. So they paid Oracle like a ton of money, and all the 10 sites that are distributed are all running Oracle. Then you call it a homogeneous architecture, homogeneous DDBMS architecture. A heterogeneous DDBMS architecture is they all have the same data model, meaning they're all doing relational databases. They all have tables, but different vendors. And the vendors, the tables can interoperate. So one of them has MySQL, the other one has SQL Server, the third one has Oracle, fourth one has SQLite, whatever. But they're all relational databases, okay? So that unites them. Then you call it heterogeneous. Heterogeneous is the opposite of homogeneous, by the way. It is heterogeneous because it is not the same vendor. There can be something called fully heterogeneous. Then it's even more interesting, where you have 5 machines, Not all of them are relational at all. Some of them are NoSQL. There's 4 types of NoSQL, by the way. So say there are 5 machines. Each of the 5 can be different. NoSQL number 1, NoSQL number 2, NoSQL number 3, NoSQL number 4, SQL 5. That is called fully heterogeneous. So just for concepts, sake, we distinguish things like that. But in general, you can do this, by the way, anytime somebody can do this, but mostly people actually stick to having the same data model. It's pretty easy to interoperate. But have different vendors. Then you don't have something called vendor lock-in. Vendor lock-in means you sign like a 10-year agreement to Microsoft and say, every year I agree to pay you $1 million and you agree to upgrade your stuff. So you basically pay sell your soul to the devil, right? That's what it's called. But then in a heterogeneous world, you don't have that. Each vendor can be different. And if you don't like them next year, you don't have to renew them. All right, so that is the whole enchilada, meaning that is really the whole deal, okay? All right, so it comes in 3 varieties. Now, those are the 3 varieties. And I already showed you the picture. In the fully distributed database, everything is distributed. Transaction processes also are distributed. Data processes are also distributed. Everything is distributed. So then how does it work? Protocols. Again, internally, they know how to talk to each other. And so then you send commands, meaning SQL commands, and also data is like flying back and forth. It's coming from DPs. But in the end, they're all put together. Okay. Yeah. Then it's a switch ultimately. So the main receiver of your transaction just knows what to forward where, and then collect them all and send it back to you. Almost like web server. Okay, so then that's what's happening. Nothing more to tell you. Okay, so then what about the restrictions? Meaning sometimes, this fully distribution idea, a site, like one of the nodes in the cluster, can place some kind of a restriction. It might have something about bandwidth limit, okay? Like, more than certain bandwidth worth of data you cannot ask me. Or you cannot request more than 100 connections at a time. So all those limits can be set just to protect that site, because maybe the site's not very powerful. So each site is allowed to have their own limits, and then the transactions would have to obey the limits. That's all. You can configure that. Limit for any number of reasons. For example, somebody might say, you cannot have any write requests. It's read only. Say they have a stock database with, I don't know, stock prices. Just like a bad example. Well, something that is only read all the time. Again, maybe a library catalog probably that is not updated that often. That's a read-only request. It just refuses to do any writing, constantly. Or number of tables. There may be a restriction that says you cannot ask in one transaction more than 20 tables. These are all set in configuration files, okay? Or even different databases. A database can be made of many tables, but how many such databases can you access in one transaction? That can be a limit. Or even the database model. Like some site says, I only have relational access. You can only ask me SQL queries. Okay, these are very interesting. You can restrictions on them, for practical purposes. And then this notion of local distributed request transactions, and then that's all it comes down to. Is your request local, or is your request itself going to be distributed? And then, in other words, is one machine making a request to a transaction process, or multiple machines making a request? That is local versus distributed request. And then what about the transaction, which is already by definition many things, right? Like many reads and writes. Can they all be local, or can they all go to different machines? So transactions can also be local or distributed. That's what all this says ultimately. So a single remote request is one statement, comes from somewhere, and then a data process it. A remote transaction is a single remote. In other words, there's a site, and you send one transaction to it, and you're trying to access all the resources from there. It's called a remote transaction. And then a distributed request and transaction is when the request is distributed, you take your SQL statement and you look at it, and wow, the SQL statement needs to run on multiple sites. Distributed request, and then it's requesting data from multiple sites as well. Distributed transaction. So they all say the same thing ultimately, okay? But so don't be confused. In the end, we're just saying that modern transactions are basically distributed. So anything that you generate on your phone, it is going to turn into multiple, like a distributed request, and then which in turn will become distributed transaction. And then it'll run on multiple machines. You'll get one result back. So therefore, when your transaction is distributed, again, you're trying to buy something from your phone. What if it causes reads and writes to happen on more than one machine? Because that is what a distributed transaction is. So how would you make your transaction atomic across multiple nodes in a cluster when you have the possibility that one or two of those nodes might not work? meaning a part of your transaction is going to fail. How would you take care of it? Okay, so this is the heart of this whole lecture, believe it or not. It is simply an algorithm called two-phase commit. So two-phase commit makes it seem like even though you have a distributed cluster, all this didn't matter. It was just one massive, just giant machine, and the user made a request, and everything ran on one machine and then came back. That's what it feels like, even though things are clearly distributed. That algorithm that makes it possible is called a 2PC algorithm, two-phase commit. And it's again a very easy idea. Many of these ideas are that simple. Otherwise, they wouldn't scale to billions of people. It just works. It has problems. It's not magical, but it works most of the time. I'll even ask you actually during the discussion what those problems might be. Okay, so then the problem we're trying to solve with the two-phase commit is called distributed concurrency control. Meaning you can say that without the distribution, what we saw in the previous lecture was simple concurrency control using two-phase locking. It's all about just transactions wanting locks, and you can use a lock manager to solve it. But now you have new problems, which is all these machines in the cluster having to communicate with each other. You have to send data back and forth, right? So what if the communication link breaks? Then what are you going to do? Then it's more than just other transactions wanting your data, right? It is simply your own transaction failing because the nodes are not able to communicate. It's a new problem, a very different problem. Okay, so it's important in distributed databases, multi-site operations, whatever. Okay, this is easy, right? But now you have, again, inconsistencies, meaning when machines need to update data with each other, and one does the update, the other one does not. It's not allowed. It's not possible for it to do the update, not capable of doing the update. You have an inconsistency. And you can have deadlocks even across machines, by the way. So some transaction in one machine has some locks. And then amazingly, part of the transaction also involves this machine over here, wanting like more locks from this lock manager. Now there are two lock managers involved and two transactions. So you have some locks, you want some locks. I have some locks, I want some locks. Oh my God, we're both like having deadlock. The deadlock is not on one machine. Deadlock is on two different machines together. Whoa, that's a distributed deadlock. All right, so we have to somehow make it all work. Before the actual commit happens, the whole distributed transaction succeeded. Wow. So now this commit would mean multiple commits. So maybe I can make this diagram a little bit nicer. A distributed transaction therefore looks like this. You have a bunch of machines that are connected. Just do a simple connection this way. And one of them is your transaction process. So you're trying to buy something. What this means is that own machine has to fulfill a part of your transaction. This machine also has to fulfill a part of your transaction. I'm going to join it back, okay? So this machine also has to fulfill a part of your transaction. So what you want has to happen here and here and here. If they successfully happen, you're still operating on local copy, local copy, local copy. So if they fully succeeded, you commit locally, meaning this is updated. You commit locally here as well. This is updated. And you commit here locally also, this is updated and tell the user, well, succeeded. Your order has been placed. So that is a distributed commit in the sense commit, commit, commit. They all have to do independent commits, okay? These processes have really nothing to do with each other, except for any data they have to send back and forth. Maybe this table calculation has to happen and the result has to be forwarded to a cell over here. Otherwise, there's no connection between them. They're independent, okay? But except your transaction is really what connects them at runtime. But how are you going to do it? Like, what if it fails is the question. What does failure mean? This is what failure means, okay? Failure means, again, the three sites that I put up here, right? ABC. Just call them ABC. The three machines on which your stuff is going to run. And the problem very simply is this. In a client-server architecture, the client sends a packet, a bunch of packets, right, called SYN packets, with some header to a server. The server would say, I'm sending you some SYN packets also, and I'm acknowledging you. And this client says, okay, acknowledgement accepted, I'm acknowledging you. And now you have a nice two-way connection and stuff can start to happen, right? This is exactly how the whole TCP thing works. Very similarly, something has to happen here. Supposing all that doesn't happen. This transaction processor says, I'm going to keep a part of my transaction. I know what to do. I'll just simply send along this transaction to B and I say, good luck, tell me when you're done. Same thing, I'm sending you a part of the transaction C, you also go. All of us, let's get to work. If you do that, something very bad can happen. Because C got the request, C is trying to do the request, and C says, oh my God, the tables are broken, database is down. Wow, I'm not able to do my part. Meanwhile, A and B both did their part, committed. Now you have a broken transaction. because you did not do this whole handshake, okay? So you need some kind of a handshake. You need some kind of a synchronization mechanism. That is what's missing if you do completely distributed. So you cannot do that. You need to make sure that they can all do it. Okay, then that is what this is. You have site A, site B, site C. So site A, C succeeded, okay? Actually, what happened here? Yeah. Okay, so sorry. What happened was A succeeded, and then A did the commit. So A works just fine. It locked the cell, wrote it commit locally on A. And meanwhile, B got its part of the transaction. It also locked Y, wrote Y, committed. The third part of the transaction was supposed to involve a cell called C. Except you tried to lock C and something went wrong. And then this local site C said, I'll throw away that part of my transaction. Imagine this didn't happen. So now you have a global problem because these already have happened. So say, X plus Y equal to Z or something. But now that changed, but that didn't change. So now you have a problem. And the problem happened because whoever is the transaction processor, say it is A, it did not check with B and C to ask, are you capable of committing yes or no? Are you ready to commit? This question. So we didn't ask that question, and so we didn't know the answer, and therefore Z failed us, okay? So the obvious answer is to do it in two parts. There's an initial handshake part, and then the real part. That is why it's called two-phase commit. So in two-phase commit, it's atomic. You try to make sure that all succeed or all fail. So how do you do that? You locally maintain a log. So what you tell each of the ABC machines, including yourself, is in case something goes wrong, we need to back out. Make a log entry of what you're going to do, and then actually go and try to update your fragment. If for some reason your update fails, and my update succeeded, I went and did the update anyway, I can go in my log and locally unroll if I want. So if you unroll, we can all unroll, then the whole thing unrolls. Okay, therefore it's called the do, undo, redo protocol. You can read about exactly what that is, but it's what I told you. So what happens is this, the two phases are like this. In the first phase is called the write-ahead protocol, where is ultimately the so-called preparation phase. So what the main node, which functions as a node that supervises everybody else, it asks the others, don't actually commit. Send me an acknowledgement saying, are you prepared to commit? Okay, so do the operation and then don't commit, but tell me before you commit, are you actually able to commit or not? So what the manager waits for is a yes from every single one of the other nodes. I have a diagram I'll show you pretty soon. It's actually here. So you have to get a yes answer from everybody that you ask, are you able to commit yes or no? It's a unanimous yes, okay? If you get a unanimous yes, including from yourself, then you send one more message back to all of them and say, no, go ahead and commit for real. Commit. Then they'll all commit. Then the whole thing is supposed to succeed. So in the first phase, if you say prepare to commit, yes, no, yes, no, yes, no, yes, no. This one says yes, prepared, yes, prepared, yes, prepared, no, not prepared. So then because of that, you tell all of these, any local change you made, unroll it. Commit didn't happen, you don't worry about it. So any local change that you made, just unroll it. So that all of them went back to as if nothing had happened. That is possible because of the initial question you asked. Are you ready? Yes or no? That is called the preparation. The preparation succeeds, then final commit happens. The preparation fails, then the one machine or the machines that failed, you have nothing to tell them. But the other machines that locally succeeded, you tell them to fail as well, meaning unroll. Everybody unroll. So it looks like this, okay? Okay, I can do this. Let's see what happens. If not, I'll just show you the raw diagrams, okay? Actually, shut up. Okay. So in here, I'll run this a bunch of times, we'll keep watching it. So A is the one that is running as a transaction coordinator, meaning it's the main machine that is controlling all the three machines, including itself. So then you can read this, okay? Maximize it, I think. Okay. So A writes a prepare T. So prepare T means, tell me if you're ready or not. So that's the third step. So first step, A sends to everybody, commit T. Prepare, sorry. So this one says prepare. Then they'll say ready. Then you say commit. So three steps are prepare, that means answer yes or no. And then the answer is ready or not ready. That's the third step. Once again after this, first step, second step, they're both ready. And then third step, you actually tell them, go ahead. You also locally go ahead. So this is success, okay? Success looks like this. There's no unrolling anywhere. But the main thing was the commit actually happened on the third step, not on the very first step. Ask a question, get an answer. Both, all n of them better be yes. And then you say commit to all of them. Otherwise, you're going to abort. Okay, so this was easy. And then what happens when you have to abort? It looks like this, okay? Let's hit the play here. Let's hit play. It's an old slideshow that I hacked together from other code many years ago, but it works. It's the same thing, right? First step. But now look what happened. C says, oops, sorry, I cannot do it. So then you tell B also abort. Everybody abort. And you should also abort yourself. You throw the transaction away. Okay, so that's what happens. It means any local changes that you made are not committed. You know how I told you, right? Commit is when changes are permanent. Otherwise, the changes are considered temporary and they can be backed up. Just look at your log and just look back up. Whoa. That's pretty much all there is to it. It's very simple. Obviously, it is not without problems, right? So I'll ask you about the problems, but it's still better than not doing anything at all like this, okay? Okay, so that is why it's an improvement. All right, so there's many ways to explain it. So we'll just spend like a few minutes on it. Okay, I'm going to read it. There are two phases. The first phase is sometimes called commit phase. Some people call it voting phase because you're asking for a vote. The vote has to be a unanimous yes, by the way. Should we all go ahead, yes or no? It's almost like in phase one. Okay, I'm going to tell you. Suppose, okay, so let's pick some colors, okay? In phase one, you're basically like a mob boss, okay? Like a terrorist boss somewhere. Oh my God. Okay, so this is a terrorist boss, mob boss calling the shots from like far away, okay? They're not doing any transaction. And then your foot soldiers, your lackeys, your bad guys, they're like all over the place. So they're all trying to pull off some horrible coordinated attack, like a multiple bombing. I mean, this series, okay? So in some places, that's exactly what they do. They do coordinated bombing, okay? But then they all communicate back to the boss and say, yes, line is clear, meaning we're ready. And then that boss sends to all of them, go. And then some massive, crazy, bad operation succeeds. If these are saying there's police nearby, we cannot do what we plan to do. There's no point in doing half of it. They're not going to get a bang for the buck. Then they'll tell them, call it off, just come home, right? Just another day. So the whole planning is off, basically is what they're saying. That is exactly what this whole protocol is, believe it or not, okay? In the first step, you're not actually doing the operation. You're just saying, can you do it? And they all say, yes, we're ready. And then the boss says, okay, go ahead. Rock and roll. Bad. But that's the first phase. You just ask, vote. Are you ready for this? So sadly, I'm going to, say that on 911, that's basically exactly what happened, right? I mean, there were multiple sites. And somehow they coordinated and they all thought they could pull it off. And they basically almost did, right? Okay. So when you plan for 10 years and do something horrible like that, then that's kind of the thinking that goes into it. Can you do it or not? So phase one is the request phase, okay? So coordinator says, can you commit or do you need abort? It's also called query to commit. Google all of these, okay? You'll come across many articles about these. But in the end, it's all the same thing. The node needs to respond. So if everybody says, we're ready, even if one of them says, we're abort, the whole thing is off, okay? Because that is what this does. If in phase one, all nodes respond with can commit, then the coordinator sends a commit phase to all of them. And then they all commit and the whole thing is done. Otherwise, even if any one of them says no, then you tell all of them, even if you're part way there, back off. It's as if the whole transaction never happened anywhere, right? Leave no trace, just back off. And so then you can start to think about this and go, what happens if this happens? But that's the reality, okay? So in the actual implementations, it's like small variations of what, how it works. But the idea is actually dead simple, right? Because, what is better than this? But nothing. So it's an all or nothing scheme, but globally. Even if one fails, we all fail. Everybody has to succeed, or else. Because in a transaction, right, that's exactly what needs to happen. You cannot be inconsistent. So in your, Amazon example, if you're not able to get, for some reason, a shipping number, then they'll put off your transaction till the next day, until DHL or, UPS or something can give them a shipping order number, tracking number. That's how this all actually works. And you don't know you placed an order and you did not get your tracking number, but indirectly somebody's making it wait, because you cannot partly, do something and not be able to give you a tracking number. Or the credit card validation. That's the ultimate thing that actually kills lots of distributed transactions. Your card that they have on file expired, and the bank sent you a new card with a different number, or maybe somebody hacked your card, you got a different number, but you forgot to update Amazon and they cannot So then Visa denies your request, right? Then your whole thing is off. You're unable to process your request. Log on and update your credit card. Then that's an all or nothing scheme. Okay, so then that's it. Yeah, so all this is so that the DB is not left in an inconsistent state. So the problem slide that I showed you early on, the very first slide, was A succeeded independently, B also independently succeeded, C independently failed. And so then now you have a problem. You try to prevent that, okay? Try. This one has a nice, like a sequence diagram, the timing going vertically like this. This is called the UML sequence diagram, just so you know. So UML is like a modeling language for describing class hierarchies of all things. Okay, so then, but in this case, you can use it to, even go time vertically. This again looks like TCP/IP, right? So this one says, can you do it? So yes, I can do it. Okay, do it. All right, done. Very cool. One way, back and forth. So you can read much more about it. And this is how we actually set them in reality. In other words, that's how the messages are actually exchanged back and forth. Okay, XML. Cool. Okay. Okay, so we're almost there. This is fantastically great. What else should I have to tell you? Yeah, so distribution. Now let's have some fun with distribution, okay? Okay, so the problem was really the whole notion of, how are we going to succeed? And we do the best we can with two-phase commit. Okay, now we're done with the main part of it. The fun part of it is, there's a song called Yes, We Have No Bananas. Okay, so we'll actually do it another time. I want to sing. So yes, we have no bananas. Yes, we have it. It's a pretty funny song. So that is what I'm trying to joke here. Yes, we have no distribution. Okay, so distribution is all the things that I just now told you, which is data can live in multiple places. The computation, the transaction also can happen in multiple places. You can have so many copies like all over the place. Some transactions can succeed in some places, fail in others. The whole thing is aborted if that happens. You can have a fully heterogeneous system with somebody running NoSQL, somebody running graph databases and what. Okay, so this is all considered distribution. The crazy amount of cool stuff is going on behind your back. You're fully unaware of it, okay? You're totally transparent to it. You're like the small little simpleton that sits in your home with your little phone and you think you own the whole world. That idea is called transparency. All the operations that are happening in the back are transparent to you. That's a very weird term, by the way, that they use. I would use the word opaque, okay? Opaque means you will not be able to see in it. Transparency is the exact opposite. Transparency means I can see everything, but that is the word the database industry uses, okay? So transparency means actually it's so transparent you have no idea what is going on. That's what it is. So there's many kinds of transparency. In other words, we can hide many things from the users. That's all it is. They're all called transparencies. I'll tell you what they are, then give you some examples. Distribution transparency is the user does not know where their data is or where your data is. Like your Amazon, again, I'm buying a book and I'm buying some pens and I'm buying a guitar. I truly don't know where those catalogs are in the world. I have no idea. That is called distribution transparency. Transaction transparency is I don't know what computer processed my credit card, what computer processed my tracking number, what computer took my order, and what computer fulfilled my order. No idea at all. Or where's my catalog? I don't know what is happening where it is called transaction. Failure transparency is exactly what you think it is. Some node in the middle of all this failed in the middle of my searching. I just had a 1 second delay, but then my screen showed up anyway. So I had no idea what machine failed. And my request went to a backup machine. It's called failure transparency. Performance transparency is again what you think it is. Some machine was pretty bogged down with requests. So it served my request a few milliseconds late. And I did not know. I'm just waiting for my page to update. This is all being hidden from us. I have no clue at all what kind of database architectures in Amazon uses. They probably have graph for recommendation systems, right? They probably have actual good old relational databases for all the money that they get. They probably have for the questions and answers, the ratings that people give, what is called a document database. So they probably have all kinds of databases, but we have no idea what they're using. That is called heterogeneity transparency. It means we don't know how heterogeneous they are. So we can just simply hide so many details, okay? Together, they're all called transparency. I would together call all of it opacity, but that's just me, okay? Because transparent is the opposite. Okay, so now the rest is simply just like more detail about all this. In distribution, there's 3 levels actually. First of all, we don't know how many fragments exist for any table. We have no idea how many tables they even have, right? A few thousand, but we don't know how many fragments. Next, we don't know how many different places in the world all of their servers are. And third, you put those together. We don't know what fragments exist on what tables. That's called location mapping. Like only the server knows, the internal server knows. That's called location mapping. Even if you knew the location, you didn't know what went where. That's called location mapping. So different, all within the same overall idea of table transparency, distribution transparency. All right, so then the way internally they manage it is the server obviously knows like where everything is, like where every fragment is, what IP address for each location. That is maintained in a table called a distributed data dictionary that obviously only the internal people have access to, the server has access to. So when you make a request, the request goes here and gets forwarded to multiple machines. You have no idea. Okay, because the backend just sends you some HTML, right? Your app happily displays it for you. That's it. So these days, all of them are completely global. They're all over the internet. And then they have local IP addresses with proxy servers. That's all you have to know. You just simply go to an Amazon proxy, Amazon.com, and you think one machine serves you, and you're dead wrong. And that's the way they would like it. So transparency, transaction transparency is, again, you don't know what is happening where. It's simple. All this. This is where the whole distribution comes in. So in the distribution, two-phase commit, something fails, you have no idea. Probably whatever machine failed, that transaction went to a backup, and then the backup said yes, vote yes. So they all voted yes again because of the backup. And then your transaction succeeded. You took just a few more seconds to complete the transaction, but you didn't know. Okay, so transaction transparency. Performance failure, again, it's what it says it is. If something is slow for any reason, or if something fails, and then your copy machine got your request and things were fulfilled anyway, and you didn't know. That is called failure transparency, performance transparency. Okay, this can happen for many reasons, the whole notion of failure or performance. If your network is slow, that is called latency. The packets are, very slow to be delivered. Occasionally your machine just spins and spins and spins. Partition means break. It means your network literally broke. It means some connection between some machines were lost, and then you still are able to, do the transaction. Suppose again, they're connected like this, okay? They're connected like that. So sorry, not that. I'll do it again. I need to do a Z actually. Suppose they're connected like that. And they're connected like that. So then what happens is if this machine to this machine usually is using this connection to do the service because it's straight, it doesn't have one hop, one extra jump, right? But say this breaks, then that is called partition, it's called partitioning. The network got partitioned. But now your request can be routed this way. So it'll still work, but it's going to be a little bit slower. Yeah, exactly. That's what I was saying, Sonia. It's weird, right? That's exactly the comment that I made. I would call it opacity, okay? So opacity is what I would call it. A black box is opaque. I cannot see through it. They're using the exact opposite term. I don't know. I think it's weird. Yeah, it's not transparent. It's opaque. Yeah, but we call it transparent. White is black. Black is white. Up is down. Down is up. East is west. West is east. So we take into account like all this. Yeah, failure means partitioning. That's pretty much all. I want to finish this up, and then we'll be fully caught up. It'll be beautiful. All right, so how do you design this notion of distributed database? Now, what do you put where is what, all this, okay? And it's very simple. Replicate means make copies just for backup purposes if something breaks. Partition means physically divide your database. So they're two different things, okay? And partitioning also means fragmenting. This is breakup tables, both horizontally and vertically. And this is just make copies, for backup recovery purposes. And then what goes where? That's the notion of designing this. Okay, so fragment, partitioning, they all mean the same. There's horizontal, vertical, and mixed, and I already told you. And it's an easy idea. So you can even do you can even combine them. Suppose there's a table, you make two horizontal fragments, fragment A, fragment B. And within fragment A, you can make some column partitioning, but just for fragment A. For some reason, you want those columns to be separated, but maybe you don't care about B's columns. B, these are more frequently accessed data or something, okay? So then just for those rows, you can make some column partitioning, 4 columns. Whereas this one, you can only make 2 column partition, meaning column A, column B. So now we can store all these 6 pieces separately in 6 different places, okay? Then that is exactly what's called mixed fragmentation. Because together, all the 6 pieces that exist in 6 different locations, all connected somehow, are exactly what you call a distributed database. So there are different schemes for, how do you put, what you put where, what. That's all. Especially in columns, maybe these columns are more frequently accessed. Maybe these columns are not that important. So they would put them in long-term storage that is pretty slow and, painful to access, because the idea would be most people wouldn't need them. But this you keep in high-speed memory, because you would need them. And together, the whole thing is these are more important than these ones. So these ones you put off on some tape drive because hardly anybody looks at these rows. You sort those rows and you think these are more important. So all kinds of fragmentation schemes are possible. And you can back up all of them. So this fragment for some reason is pretty important, okay? You can make like 4 copies of these. And this one, you only make 2 copies. And all of this is highly important. So make 8 copies of all of them and put them all over the place. In other words, they're all entirely separate things. The notion of replication, which is copying, and fragmenting, which is breaking up. So you do it by, again, what the database is supposed to do, all just based on what the tables are. But in the end, that's all it is, okay? So rows are broken, columns are broken. You can do one followed by the other, just alternate. Row, column, breaking. Then you have mixed fragmentation. Replication is just copies. So after you fragment, you make copies for things like load balancing. So you can send a part of the world to one copy. You can send another part to a different copy. Or if something breaks, you can then use the backup as the main machine to reroute all the requests and then fix the broken machine so that you have multiple copies again. Yeah, exactly, ironic scientist. That's right. So in replication, the main thing is pretty simple. I want to finish with this, okay? Take a few minutes. Okay, so in data replication, it's all about consistency. The more copies you have, the more you have to worry that all those copies and the mean will all always have exactly the same data. Otherwise, you have multiple versions of the same truth. Then why even make copies? Then you're misleading people. There's a funny saying that says a person with one watch, they know the time, right? So here's your wrist and here's your watch. You can always look at the time. If you're wearing 3 watches, okay, for some crazy reason, you wear 3 watches, in general, you look at the time, they're all going to give you 3 different values. This before the atomic clock, okay? Then you never know what the time is. Okay, that is exactly the problem with replicating. So when you have copies, supposing the copies can all be independently updated, okay? Say it's the Amazon catalog. There are 4 copies of the catalog overall. There's 1 main and 3 different copies. Product managers can update something here, or update something here, or update something here, or update something here. Now all hell breaks loose, right? Because now what we should ensure is as soon as this update is made, that update should be communicated to all of these other copies as well, so they all have the same update. Then it doesn't matter where in the world people order from. Otherwise, you have a problem. If somebody orders from here, they have $10 off, but not $10 off when you order from here. That is the notion of inconsistency, or what is called mutual consistency. They should all be mutually consistent. Likewise, this change should be propagated to here and to here and to here as soon as possible, so that they all become synchronized. Like see in Dropbox, right? They do it automatically. Any change that I make, it's up to date. I love that, by the way. I'm paranoid. I keep watching it. So any tiny change I make to my file, instantly I see a little blue thing spinning and says up to date. That is what we're talking about. So you need some mechanism like that that constantly does updates. At the same time, any little cell value should not cause a whole flurry of requests, okay? So there are update requests. So there are 2 kinds of updates that can happen. One is called a push update. The other one is called a pull update. In a push update, the machine making the change should push the change out to all the other machines, all the other copies, and say this table, this row, this column, this value changed. Exact same change should be made by all the machines as soon as possible. Until then, temporarily, things are inconsistent. But you push your changes out to other people. I make a change, I push my change. I tell all of you my email change, please update. Okay, it's my responsibility. On the other hand, a pull request is the opposite. Pull means periodically, a machine will send a request to all the other machines and say, did something change? Did something change? Did something change? Yes, I changed this table cell, what? Yes, I changed. Yes, I changed. And then you can make the change. So I'm asking other people to pull requests back. It's called the pull update. One is not inherently better than the other. Just pick one, but do it. All right, so the fragments need to be identical. Push, pull helps. This is all because, in case this data loss happens, they should all be equally ready to contribute their copy, because it doesn't matter what copy you pick. Otherwise, if the copies are stale, then you really lost data, right? Because one of them updated and it broke, and then the update was not communicated, meaning the others didn't make the update. So now you literally lost data. So you need to be paranoid about always maintaining mutual consistency. Yeah, I guess so. That's one way to explain that, right? Yeah. I don't know. I mean, I like that actually. Yeah, so this is actually a very cool answer. The UI, including the fact that you have this one single looking page, it's a shopping cart, has got 5 stars. That makes it seem like all the stuff in the back is, doing like weird stuff. So the design is made, the interface is opaque, and then everything else is transparent here. In movies, we call it suspension of disbelief. Okay, so when you go to movies, you need to suspend the notion of disbelieving everything. Like, oh, that can't possibly be real. He didn't shoot her, did he? You shouldn't ask those questions. You should just be part of the story, right? So it's a little like that. You want to be transparent to what is going on. So that is a suspension of disbelief. Yeah. So I think I like that answer. Okay, so very little to finish, and we can take a break. A fully replicated database is every fragment that you make, all the fragments that you made, all the pieces that you cut up, should all be backed up somewhere. And hopefully, that's what everybody does, because then you think all your data is important. Then it's called a fully replicated database. All the fragments have a copy somewhere, so it doesn't matter what fails, and you can always get it. On the other hand, a partially replicated database might be, maybe I told you, maybe only the top rows are for some reason more important than the bottom rows. So I'll only take this fragment, that fragment, that fragment, and replicate them twice for this fragment, and then this fragment I'm replicating 3 times for some reason. Maybe I love those columns. These columns I don't care about. I replicate only 1 time. On these rows right here, no replication at all. So now it's called a partially replicated database or table, because you're not replicating this at all, because it doesn't matter if it goes away. Madness, right? So you call it partially replicated. Some fragments are copied, but other fragments are not copied. And this is sheer madness. I have my entire company in my 0.5 terabyte flash drive that I have in my hand. And if I, sitting on the toilet and it falls out of my pocket, there goes my business, okay? So we never do that, okay? We never just have unreplicated databases. It's like a fantasy. But if you ever do it, then you deserve every problem that happens to you. And then it's called unreplicated database. So replication is a cool idea. In general, you must replicate, obviously, right? Because danger, lurks everywhere. You should be prepared with backup copies, fully updated as soon as possible. If you can read. Oh, this is a huge thing that I'm not telling you, but I already told you actually. Okay, so just going on and on and on. The same idea, okay. All right. It tells you here, like, so disadvantages of no replication. Like, what the hell? Everybody go away. Okay. So look, data is not easily available as there's no replication. The data is permanently gone as there's no replication. Okay. Wow, 3 slides, almost when I should be stopping. Yeah, then how do you store these fragments and replicas? Again, if you say centralized data allocation, then this is bad again, So if you put all your eggs in one basket, suppose you put all your copies even in just one central location, and then the building goes down, there's an earthquake, or the basement is flooded. So the whole basement flooding of servers, by the way, it's a real thing. So I'll show you, okay? We just say basement flooded, right? Server room. This is a real deal, and it's horrible, okay? Sometimes what happens is you have, because of fire reasons, my God, look at that. It's horrible. For fire reasons, sometimes you have actually water sprinklers on the top. In the middle of the weekend, when everybody was home, there was some leak. It's not this bad though, but that can actually destroy a part of your server. Because you come back in the morning and you go, oh my God, what happened? Look at that. Water coming out of your machines. This is like, oh my God. Okay. Somebody's bad day right there. And somebody's problem to, bring it all back up. The CEO says, in how many hours can you bring it back? 4. Fuck that. 1 hour. Yeah, so this happened, right? Exactly. So you guys actually could not even you couldn't register for classes, right? That was actually amazing to me. Thankfully, USC didn't do that. Some contractors actually, they're working nearby. They broke some pipes by accident. Yeah, stuff happens, okay? Anyway, so that is the reason why you never do centralized data allocation. Okay, so then this one just simply is partitioned. Is you partition your data into multiple fragments, and then you store them, but no copies. But this is the best. You partition and you copy. So the last is the best of all, okay? Fragment and make copies of fragments. Hopefully fully distribute, meaning fully copy it, full replication. So every fragment is in more than one place, and then you're hopefully got. Okay, statistically speaking, again, all those places where you have copies will all not be gone. You might know about Iron Mountain, okay? So Iron Mountain is actually a company. Who knows about Iron Mountain? Iron Mountain Locations. Yeah. So this is a company that literally takes Microsoft source code or Apple source code and buries them deeply inside the mountains in parts of the world. That is how serious they're about data, okay? Oh my God. Yeah. So that is how paranoid you have to be to protect your data if you really need to do that. That company makes its whole living doing that, okay? Iron Mountain. Yeah. So if you give them a copy of your database, they'll guard it like it's their life, basically. because they give you a service guarantee. They'll give you all your money back if for some reason they screw up. God knows how deep these things are, and needless to say, there's no drop of water anywhere or fire danger. They actually have fire sprinklers everywhere, so your data is not going to burn, okay? But you pay them money like crazy to do that. You can read about it. It's pretty fascinating, actually, the business. The whole business consists of guaranteeing to you. You give us your copy, we're going to hold on to it. Yeah. Okay. So, replicated data. 2 more slides. The CAP theorem. We'll easily do this, on Thursday, next week as well, because I don't want to rush it. But this notion of CAP, it's not a theorem, first of all, right? It's simply a principle. So someone called Eric Brewer, who's actually a UC Berkeley, professor, database professor, he made an observation, back in the 80s. He actually gave a talk about it, called the CAP theorem. He just simply called it, and it caught on. What he's saying is ultimately any database, especially distributed databases these days, cannot simultaneously give you a guarantee that all these 3 things that are named here would all be simultaneously high. In other words, as soon as an update happens in one machine, all the 1,000 machines, they all instantly get updated. That'll be a high consistency guarantee. High availability guarantee is anybody can wake up in the middle of the night anywhere in the world and log on, or one of those multiple copies that we have will actually give them immediate access, meaning we never bring machines down. So availability means the machines are never down for any reason, for maintenance reasons. It's always up. That is a high availability guarantee. A high partition tolerance means I basically guarantee that my machine would always be up, my network would never fragment. That is what the theorem says. It means you cannot get all 3 equally high. Only 2 out of 3 would be very good, okay? That's what CG is trying to say. Yeah, you only get 2 of the 3 CAP options. In other words, if you want high consistency and high availability, it means you have to sacrifice partition tolerance. If you want high availability, this is basically what all internet businesses do, by the way. They want availability at all costs. They never want Alibaba.com to ever go down, Amazon.com ever go down, at the sacrifice of consistency. In other words, because things are highly available, I can order something, you can order something, neither servers go down. But your server got some price changes made. They'll not bring my server down to update the price change. They would rather suffer some inconsistency because they don't want to lose my business. See, in reality, partition tolerance these days is actually not a big issue, okay? So we actually take this out. I'll put up some things on the extras, tonight you will read. It has come down to C versus A, actually. So rather than 2 out of 3 for CAP, it is more like 1 out of 2 for CA. Like, do you want high consistency or do you want high availability? And here's why you cannot have both. High consistency means this. As soon as I make a change in one machine, I need to make a change in all the other machines. So I need to shut them down and actually keep people out. Availability has to suffer. Then when I bring you all back up, then you will have no consistency issues. All of them are the same data, really. So that is pricing consistency. On the other hand, pricing availability, which is what every business does, is they leave the machines on all the time. So then if somebody makes a database change somewhere, then sadly the consistency would have to wait. And they would do it as soon as possible, obviously, they bring it. That is called soft consistency, okay? So then when you have high availability, low consistency, it is called basically available. Soft eventual consistency should be called basic, actually. Soft eventual consistency. It's all about consistency, okay? So then that is what happens. So the internet world chooses pretty much base, whereas the old timers who love data very much and relational tables choose consistency. You don't mind shutting a whole building down. Like say you're a Bank of America, they would send an email in the middle of the afternoon. Server going down in the next 10 minutes, won't be up for half an hour, go get coffee. Yeah, then nobody could log on. They're making some updates, okay? But they could get away with it because they only had a building full of users. But now you have a world full of users. They couldn't give a rat's ass, right, about your consistency. So they'll go somewhere else. So availability, the customer is king or queen. Okay, that's all it is. So consistency, always correct, always fulfilled, and then always operate. So even if some part of the node is broken, you still think that you can fulfill the request to other nodes, okay? Okay, so CAP theorem used to say 2 out of 3, you can read all this. But then in the world of ACID, all that just goes away. You price consistency above everything else. But in today's base world, you want more of the availability, and then rather you sacrifice, you prefer to sacrifice consistency. You don't want to lose business, that's why. Okay, then you can read this. So in a centralized database, highly consistent because there's only one copy. One copy is not even called a copy. One version of the truth. highly available, and then partition, there's no network. Relational database, highly consistent. So this is the old world, okay? So the main difference really is this high versus that. In the old days, tables are highly consistent because the whole world relies on that. But nowadays we come along with NoSQL, so consistency, consistency, who cares? Highly available. Okay. Whereas here is the opposite. You see that right there. That. Others are all just detail. Okay. All right. With that, these commandments are not again commandments. So Dade is a database. Very interesting, that name, right? He's a database researcher. Probably he wrote a book that you probably used in your undergrad course, possibly. Database systems. So he simply named a bunch of checklists. Okay, so if you're a distributed database, designer, you would try and check off as many of these as possible. That's all it is. So nobody says you need to get all 12. It's not Moses, Sermon on the Mount or anything. Local site independence, it means each site can basically maintain a copy of its own database and do its own local backup, right? So others would not know, and that's a good thing to have. So central site independence means you have no central coordinator. It's highly distributed. So if that fails, there's no problem that everybody goes down. So we can have that. Failure independence, again, if node failures happen, you can reroute your requests. That's good to have. Location transparency, the users cannot know where all your data lies. It's good. Fragmentation, people should not know where, these all things I already went through. People shouldn't know where your fragments are. It's good. You don't know how many copies and where they are. You don't know what happens where. The whole transaction is basically the query. There's a slight difference between query and transaction, meaning your query is ultimately your SQL query, but your SQL query gets brought. This is a higher level, lower level. So at the higher level, we should not know where your SQL is going. At the lower level, you should not know what tables are being read and written. And then the user should not know what operating. This nobody even cares, right? What hardware is being used, like Linux versus Mac versus PCs. And then nobody should know what OS you're using in Windows versus Linux, I guess, or what kind of networks you're running, and then ultimately what kind of vendor, what kind of database model. So all of these we went through before, okay? If you can design a distributed database, we have made sure that all these are true. Then you have a highly good design. That is basically what Dade said. So he called it his 12 commandments of distributed DBMSs. You can even Google it, and then we can stop with that, okay? So the checklist is all. So it's so many sites literally, right? You can read them, much more than I can tell you. But I was giving you the summary, okay? So this. All right, so I'm pretty happy because we're about 10 minutes late, but I was able to get caught up because in a way it's a weird feeling to say, wow, I'm pushing something more after the next time. But this is very good though, because look what we have next time. This is wonderful because what happens in between a web server and an actual database? So how does the backend work? That's what this is about. And this is how do we make all of this as fast as possible? Because no matter how fast your network and machines are, users still want speed. How do you do that? And then this goes into data warehousing. It's the beginning of data science actually. And then spatial database, new kinds of data. And then it's all a new NoSQL world from there on, okay? So it's pretty neat. So we're at a very nice stopping point. We can take a 10-minute break. We can come back at 8:01. And then for approximately 20 minutes, I will ask you some fun questions for discussions. Okay, so we can do these when we come back at 8:01. Okay, bye. Stop. I'm leaving. Yay, and we're back. Okay. So I'm going to ask you some questions, okay? So let's answer. These are all fun. They cover a bunch of things. They go back a little bit to SQL, actually, just a tiny part, but then more about transactions, and so forth, okay? And so they're more like thought questions. They're not hardcore actual things we went through because during the discussion, you guys can talk and tell me things. Okay, so 74 participants, chat, okay. People can hear me, right? Can someone just say yes, please? Okay, cool, thank you. All right, so I'm gonna click here, right? And then see what happens. Week number 6, discussions. So let me ask you, at least half these questions. This is cool. Okay, so this object-oriented programming, right? SQL is not an object-oriented programming language. So what oriented programming do you think it is? I didn't mention it. I want to know if you remember. Then I'll ask you more questions. So SQL, SQL would not be procedural, believe it or not. A procedural is more like a C programming language, you know. You're all pretty close, but there's a different data probably comes closest, but what kind of data? Like you're not asking each row, what are you doing, right? In SQL, you're just saying, like, look at the student table and give me all the top GPAs. What is that called? It's not just one student. It is you're operating on set, exactly. So it is actually set-oriented programming, okay? You simply ask a query for the entire set, and then the system loops through the set and returns you the results. So it's called set-oriented. Okay, so then there's set-oriented, obviously, there's object-oriented. There might even be function-oriented, right? Functional programming. But then there's one more oriented programming. I'm trying to see if somebody could actually get that. It starts with the letter A, okay? So what do you think it is? There's some programming. In fact, it's not a separate thing by itself, meaning there's no programming language for it, but it is actually implemented in Java. So I'm going to play Hangman, okay? So database, essentially a hash table. Not really. Parts of it might be the indexing part of it, but not the whole database.
I'm guessing S.
Yeah, sure. S is good. S, and then what? Oh, cool. Karishma wrote the whole word. Yes, you're both correct. Aspect-oriented programming. This is very cool. Okay, you guys can look it up. So an aspect would mean this. So suppose there's a program, and the program is doing 3D printing. It is also doing some emailing, and it's doing some, thing on a projector. It's doing like lots of multimedia operations. I can write classes that actually tie all of these aspects together. So I cut across the whole. It's called cross-cutting. Okay, so you cross-cut across all the existing class hierarchies and make like a new interface that only contains the classes that are useful for your aspect. That is called aspect-oriented programming. Okay, cool. So that should be enough. So set-oriented, aspect-oriented. So what about pattern matching? Just very briefly, this is pretty cool, right? SQL has the % command to match what? In SQL, suppose you have a string, then % is used to match what? And then also an underscore is used to match what? Yeah, exactly. % is like star, meaning match like 0 or more characters, right? What about an underscore? It matches exactly 1. Yes. So I like the question mark because in Unix it's a question mark, single character. Yeah. So many SQL implementations would support this, but they have there's a whole regular expressions language. Okay. So if you're new in order CS, maybe our databases, then you have this notion of regular expressions, and that is what this is. So you can just literally go into any site and pull any text. So let me actually ask you, how do you check for all the uppercase characters in here? Suppose you have this. Just keep it very brief, right? Probably know this. Okay. So then, suppose you want to highlight like all the uppercase, then how would you do it? Like in other words, what is the pattern that you insert? It's called pattern. Regular expression is a language that's full of patterns, okay? Magical looking patterns. Hey, cool. Pretty simple. That's called a range, okay? When you have a dash like that, it's a range. So match anything that is like uppercase letter. What about match anything that's uppercase or lowercase? Now what would you do? What notation for or? What if you do this? So if you have uppercase range and then followed by lowercase range, that's followed by, and that's exactly what it does, right? State finds all the uppercase. Yeah. So can you actually do an or? That's very interesting, right? So that'd be the first guess. That's a very good guess, by the way. So it's actually not or. By the way, you could do like a lot of different things. Okay. So find out what comma means. So I want you to okay, so let's try them all. One of them would have to work, right? Yeah, how do you do or? Okay, let's try plus. I mean, I might be misleading you because it might actually be what is called a capture group. So, you might need to put a parentheses, here, right? And then there's a capture group. So I can make one capture group just for this one, but maybe I can make 2 separate capture groups, right? So now we've gone back to what we had. But then maybe what if that's a separate capture group? So I'm not going to give you an answer. So it's still the same as before. But definitely try this, okay? So I want to tell you. But it's so cool you can make them all light up. Okay, so what about something else? What about not numbers? No, actually we're losing time. Okay, so I'll tell you what. It's okay. Just say regex examples. Okay, so please at some point go through it because it'll come in handy somewhere in your CS career. At some point, somebody's going to have you write something like that so that it goes in SQL and does that for your cell values and picks out valid email addresses or telephone numbers or social security, anything that has a pattern, you'll be able to find it. Okay. So my point is you can try all of those. That's valid like URLs actually. So neat. You can practice them by having some good and bad ones and see if your expression matches the correct ones. Okay, so in SQL you can do. What about more data types in SQL? Currently, we only have number, date, Boolean, character strings. What if you want to introduce like a complex number that has both a real value and an imaginary value? Any idea on how you might do it? I didn't tell you this, but would you know? Not ASCII. ASCII would be just a character set. Yeah, custom type, like a class definition. Just like in programming languages, you can make your own class. It turns out that in SQL also you can make your own class. And then you can make objects of that class, meaning your column types can be any custom type that you want. This is how spatial databases are written, okay? In spatial databases, you can make a class that is called a location or a coordinate, another coordinate class. It has two component columns, member columns, called longitude and latitude. That's pretty much it. Yeah. And many more, for sure. Yes, exactly. So that you actually do that for your homework, okay? Yes. But then in general, you can write them. This goes back to SQL. So in SQL, all the tables are just absolutely complete closure oriented, meaning any table operation you do, suppose you take a table, union compatible with another table, you'd union them. You get a long table like this. If I do a project operation and I get a project operation, then I get a smaller, thinner table because I threw those columns away. That is closure, right? You can keep on going. So what are some data types in the real world that you would use? They have closure. For example, suppose I give you plus minus multiplication division. Then what simplest data type offers you closure based on that? Meaning any operation that you do with the data keeps coming back with the same kind of data. Yeah, just numbers, right, in general. Yeah, floats, exactly. Not ints, by the way, right? Because if you divide like 5 by 7, the result is not an int anymore. I would say float, meaning real numbers, okay, real numbers. What about square roots? So if you include square root, then what is the data type? Meaning what is the kind of a number system that is also closed under square root operation? Exactly. Very nice. See, because of negative numbers. If you still think it is float, that might not be true because -5 is not a float anymore. So you have to expand your number system to include imaginary. Very good. Okay. So then you have other things like real numbers, rational numbers. So you understand closure. These are all closure. What about a data type where many operations actually give you closure, but then a few operations don't give you closure? Just like tables, everything that Cord named had closure. But column operations don't have closure anymore. Likewise, something that is very commonly used in physics and math, okay? A real number possibly, yeah, exactly. A real number would not have closure with things like square root, okay? So you're right. But what about something else? So forget just simple numbers, okay? What about something else, maybe a little bit more involved that we use, where many operations actually give you closure, but some operations don't, they break closure? What about in physics? You have a plane, you have a plane normal, and you have some traction this way, just giving you some hints, okay? Not that though. So it's not about Newtonian vector, is what I was looking for. A simple vector data type, okay? Vector is closed under many operations. If you scale a vector by a scalar, it becomes bigger or smaller, that is closed, okay? If you negate a vector, that is also another vector. If you add two vectors together, you'll get a third vector that is also closed under the addition operation. If you do a cross product, again, two vectors, you're going to get something perpendicular. I'm just going to go like that. That is also closed. So what is not closed? Exactly. So CG is absolutely right. When you do a dot product between two vectors, right, it is the length of this times the cos of this angle. That becomes a simple number. At that point, closure breaks down. So the dot product breaks closure for the vector type. Good. What about another highly related? It's almost like a vector, but a little bit more involved. Data type that we commonly use, especially in machine learning. Exactly. So both of you, matrix, very good. So under many operations, matrix is closed, right? For example, you scale a matrix with a scalar and then do that transpose of a matrix. Inverse is not always defined. That's a different problem. So sometimes inverse is not defined. But then at what point would a matrix actually, what operation would not give you a matrix anymore? Exactly. Wonderful. A determinant, right? So when you do a determinant, then that becomes a single number. That's basically the volume of this axis, right? Good. So then that breaks closure. So think of all these fun examples, okay, where there's closure and no closure. Closure is a fascinating idea. When you have closure, you can do function composition. You can chain your code, just keep going. Okay, so it's useful, but you don't always have it. In real life, what are some things that have to be absolutely done one at a time? Not databases at all. You must do them sequentially. Transactions, they look like transactions. You do this commonly, go to Starbucks and you stand in line. So when you stand in line, yeah, exactly. When there are multiple servers, that's different, but still only one line, okay? So it's almost like a sequential transaction. What are some others like that? There are some things that you would have to basically do like one at a time. Yeah. Uh, going to the bathroom in an airlines, right? The bathroom is always like one person thing. DNA processing, wow, I have to think about what that means. It's fascinating. Any customer handling, yeah, mostly it's about customers, okay, for sure. Okay, I'm going to keep going because I want to actually do a little more. So in real life, when do multiple things happen? These can involve databases. In other words, what are some purchasing things that you do in the world where many, many people are doing the same thing? Any number of examples. I named some of them. You can name them again. Yeah, sure. Yeah, again, some hot product goes on sale, right? Your next Apple, Sony PlayStation. Absolutely, so many people want it. Or even eBay auctions, right? Your food orders. That's correct. Yeah. Buffet. I like the buffet idea. Yes, in a buffet you can say, I'm going to remember that. That's a cool deal right there. Yeah, Facebook posts, exactly. So you can see other people typing as you're posting, right? Wonderful. Yes, I was hoping somebody would talk about Lyft, right? In busy places, the few drivers that are out there. Yeah, this is again wonderful multiplayer gaming. Yeah, so these are all great examples. Okay, good. And then, okay, so this is about database update. Okay, I mentioned a problem called lost update, where I write a cell value and then you come and overwrite my cell value. And then I mentioned something called inconsistent analysis, where I'm just updating a cell constantly. I'm not done updating, and you're reading as, yeah, I like that. Garima. And then I'm reading it multiple times and getting bad values each time because you're constantly changing it. You're not done yet. So there's one difference though between the database state in this versus this. So what is the difference? It's one pretty serious difference between when this happens and between when this happens. They're both problems in the sense, they're both giving you some bad results, but one is worse than the other. Log. Log. I know what you meant by log, Garima. Log. Like think about the actual tables themselves, what is happening in either case. The database, yeah, right. In which case it is still accurate. Yeah, you're right. Shimali is totally correct. When you do this, right, you're just reading bad data, and so your report's going to be bad, right? But your database is totally fine. But here the database is not fine. So yes, Shimali is 100% correct. What about this one? Suppose you have 5 people wanting to do stuff, right? They're all being interleaved. Then if you are serializable, that means, each one of them would go like independently, right? One at a time. How many different permutations exist? Say for 5 of them. Exactly. Easy, right? 5 factorial. Because you can draw a little box and says the first one has 5 possibilities, the next one has 4 possibilities, 3 times 2 times 1. Good. So in general, when you have n different transactions that are serializable, they can go in n different ways. By the way, that is not actually what serializable means, just so you know. In other words, in the real world, if you try all those n different ways, you will have n different end results of the table. Only one of them is correct, possibly, okay? So just because in theory there are n different n factorial combinations, not all of them are valid, okay? But mathematically there are that many. Okay, then this is a different question. Okay, so this whole serializability is always a problem because we're trampling on each other's, data. So what if you just simply just go the whole hog and say every time, every single serial ever in any database ever is always serial? So what is the problem with that? Yeah, exactly. Yes, all of those. Exactly. Good. You guys all totally get it. Yeah. It just blocks the heck out of everybody, That's all. So it's not workable. Yes, exactly. So maybe with 10 people, that's not so bad, but with 10 million, it is actually a problem. So Jeff Bezos will start to see his numbers go down, right? Oh, okay. So then this is very good. A serial scheduler, okay? So supposing you are able to, do something serial like that, right? Suppose that's possible for a small database. Is it an optimistic thing to do or is it a pessimistic thing to do? Can you correct? Yes, they're pessimistic. Yeah, so it is pessimistic, right? Because you assume that there's going to be trampling that'll happen. If you think that these n people are all doing n different things on your table, Then just let them all go at the same time. Yeah, Sid is pessimistic. Okay, good. This is the question I wanted to ask you. We still have a few minutes. Oh my God, maybe I'll start with this, next week. But look at this. This is a time when we had all of the locks and then we released all of the locks one at a time, right? I'll just ask you about this part. What happens, yeah, right? What happens when you release the locks one at a time? What could possibly happen? Okay, so it's not the problem about, we're not talking about this at all, okay? We're not talking about this at all. But what can possibly happen when I release locks one at a time? That means other transactions somewhere else are starting to get those locks. Maybe some transaction here had already those, right? The moment it got this, that started doing its thing. But what could happen because of that? In other words, only when we reach this stage are we fully done, okay? In the meanwhile, we could commit. So commit means make all these changes permanent. Or we could actually abort. So when you abort, these cell values that they're trying to read because of these locks could actually go back to some older state, okay? So because we're still not done like writing. So the problem with releasing locks one at a time and somebody grabbing them basically and starting and running off with it is that you might go back and change your mind. Meanwhile, they got bad data. So that is, yeah, thank you. That is actually a problem, okay? So then to stop that problem, we'll basically hold on to all of the right locks and release all the right locks all at the same time, but only the right locks, because that is, what you could go back and rewrite. When you do that, I'll finish just in 5 seconds. When you do that, that is called this middle part, okay? It is called strict two-phase locking. You can read about it. And afterwards, in your mind, think about what can be even stricter than that, okay? Like, what about that? This right, what about read? So why do you also want to release read all at the same time is the question, okay? If you do that, it is called strict. It's called strong strict. We'll come back and then continue with that. Okay, you guys, so take care and see you next Wednesday. Bye. I'm out of time, okay? See ya. You're welcome, Karishma, Sonia. Then you can hang up anytime. Christian, Vaishnavi, Echan, Shreya, cool. Shreya, I'll write back to you, I promise. With Harshit, Malaki, Sridog, bye-bye. Tian, bye to you as well. Garima, Tata, I like that. You how? Okay. Good night, everyone. Leave.